Welcome to our full guide on the Big Bang, the event that started it all. In this video, we'll take you on a journey through the history, evidence, and implications of the Big Bang Theory. First, we'll explore the origins of the Big Bang Theory and why it's considered the leading explanation for the birth of the universe. We'll discuss the key moments and discoveries that have shaped our understanding of the Big Bang. From the initial singularity to the rapid expansion of the universe, we'll cover the critical early stages of cosmic development. We'll delve into the concept of cosmic microwave background radiation, a crucial piece of evidence supporting the Big Bang Theory. Next, we'll explain how matter formed in the early universe, leading to the creation of the first elements. You'll learn about the different epochs in the universe's evolution and how they've contributed to the structure we see today. We'll explore the ongoing expansion of the universe and what it means for the future of cosmology. Finally, we'll touch on the mysterious forces of dark matter and dark energy, and how they fit into the Big Bang narrative. So, let's embark on this cosmic journey and uncover the secrets of the universe, starting with the Big Bang. At the beginning of time, the universe was condensed into an extremely hot and dense point known as the singularity. This singularity contained all the mass and energy that would eventually form everything we know. The concept of a singularity comes from Einstein's theory of general relativity. In this theory, a singularity is a point where gravitational forces are so intense that space and time break down. This initial state was infinitely small and infinitely dense. It's hard to imagine, but every particle and piece of matter in the universe was once squeezed into this tiny space. And during this moment, the laws of physics as we know them didn't apply. The conditions were so extreme that conventional physics can't fully describe what was happening. The singularity marked the beginning of time and space. Before this point, there was no before in the traditional sense, as time itself started with the Big Bang. Scientists believe that the universe emerged from this singularity in an event called the Big Bang. This explosion set off a rapid expansion that created all the matter and energy in the universe. One of the key ideas here is that the Big Bang was not an explosion in space, but rather an expansion of space itself. Space expanded faster than the speed of light in the moments following the Big Bang. This rapid expansion is known as cosmic inflation. It occurred in a fraction of a second and set the stage for the universe's continued growth and cooling. During inflation, the universe grew exponentially. This means it expanded at an incredibly fast rate, doubling in size many times over in less than a second. The concept of inflation helps explain several important features of the universe. For example, it accounts for the uniform distribution of matter and the large-scale structure of the cosmos. The energy from the Big Bang was transformed into various forms of matter and radiation. As the universe expanded and cooled, particles began to form and interact. In these early moments, the universe was a hot, dense plasma of particles. Protons, neutrons, and electrons were forming and colliding at incredibly high energies. As the universe continued to cool, these particles began to combine and form the first simple atoms. This process eventually led to the formation of more complex structures. Understanding the initial singularity and the conditions of the early universe helps scientists explain the origins of everything we observe today. It provides a foundation for studying the cosmos and its vast complexities. The story of the singularity and the Big Bang sets the stage for the next steps in our journey through the history of the universe. From these humble beginnings, the universe has evolved into the vast and varied cosmos we see today. The inflationary period is one of the most fascinating aspects of the Big Bang Theory. It refers to a brief and extremely rapid expansion of the universe immediately following the initial singularity. During inflation, the universe expanded exponentially, growing from a subatomic size to something that could encompass galaxies. This took place in an incredibly short span of time, less than a trillionth of a second. The idea of inflation helps to solve several major problems in cosmology. One of these is the horizon problem, which questions how different regions of the universe appear so similar in temperature and structure. Inflation proposes that these regions were once close together, before expanding rapidly. This allowed them to reach a state of equilibrium, explaining their current uniformity. Another problem addressed by inflation is the flatness problem. This concerns the precise balance between the universe's expansion rate and its overall density. Inflation stretched the universe to such a large extent that any initial curvature would have been smoothed out. This is why the universe appears flat on large scales. The concept of inflation was first introduced by physicist Alan Guth in the early 1980s. His theory provided a compelling explanation for the smooth and homogeneous nature of the cosmos. The inflationary period also generated tiny quantum fluctuations. These fluctuations were stretched to macroscopic scales and later evolved into the large-scale structure of the universe. These initial quantum fluctuations are thought to be the seeds of all cosmic structure. Galaxies, clusters, and superclusters grew from these tiny irregularities. Inflation also predicts the existence of gravitational waves, ripples in space-time produced by violent processes in the early universe. Detecting these waves can provide further evidence for the inflationary model. Observations of the cosmic microwave background radiation support the inflationary theory. Tiny variations in the CMB align with the predictions made by inflation. Scientists continue to study inflation to understand its nuances and implications better. New data from telescopes and space missions aim to test the predictions of inflationary theory. The detailed mechanism behind inflation remains one of the biggest questions in cosmology. Researchers are exploring various models and scenarios to explain how inflation occurred. Despite these mysteries, inflation has become a crucial component of our understanding of the early universe. It bridges the gap between the chaotic conditions of the Big Bang and the structured cosmos we observe today. As we delve deeper into the inflationary period, we uncover more about the forces and events that shaped our universe. This knowledge lays the groundwork for exploring the next phases of cosmic evolution. Following the inflationary period, the universe continued to expand and cool. As it cooled, conditions became suitable for the formation of fundamental particles. Initially, the universe was filled with a hot, dense soup of quarks, gluons, and other elementary particles. These particles were constantly interacting and colliding at extremely high energies. Quarks are the building blocks of protons and neutrons. During this early phase, quarks combined in various ways to form these larger particles. Gluons, which act as the force carriers for the strong nuclear force, played a crucial role in binding quarks together. This process is known as hadronization. As the universe cooled further, protons and neutrons began to form stable nuclei. This period, known as nucleosynthesis, occurred within the first few minutes after the Big Bang. During nucleosynthesis, light elements such as hydrogen, helium, and trace amounts of lithium were created. These elements are still observed today and make up much of the universe's ordinary matter. Electrons, another type of fundamental particle, also began to combine with protons and nuclei. This process eventually led to the formation of neutral atoms. Prior to the formation of neutral atoms, the universe was a hot plasma of charged particles. Photons, or light particles, were constantly scattered by these charged particles, making the universe opaque. As electrons combined with protons to form neutral hydrogen atoms, the universe became transparent. This event is known as recombination and occurred about 380,000 years after the Big Bang. Recombination allowed photons to travel freely, leading to the release of the cosmic microwave background radiation. This radiation provides a snapshot of the universe at that early stage. The formation of fundamental particles set the stage for the development of more complex structures. Over time, these particles would clump together under gravity to form stars and galaxies. The interactions and properties of these fundamental particles are described by the Standard Model of Particle Physics. This model provides a comprehensive framework for understanding the forces and particles that make up the universe. Experiments with particle accelerators, like those at CERN, help us study these fundamental particles in detail. These experiments recreate the high-energy conditions of the early universe. The discovery of the Higgs boson in 2012 confirmed a key part of the Standard Model. The Higgs field gives mass to fundamental particles, a crucial aspect of their behavior. Understanding the formation of fundamental particles gives us insight into the basic building blocks of the universe. It helps explain how the complex structures we observe today evolved from the simple, hot, and dense state of the early universe. As the universe continued to expand, it also began to cool. This cooling allowed for the formation of more complex structures over time. In the initial moments after the Big Bang, temperatures were unimaginably high. As the universe expanded, these temperatures dropped significantly. This cooling process was crucial for the formation of atoms and the eventual development of stars and galaxies. Without cooling, particles would remain too energetic to form stable structures. The universe's expansion is a key factor in its cooling. As space stretches, the energy density decreases, leading to lower temperatures. One of the most significant milestones during this period was the formation of neutral atoms. This happened about 380,000 years after the Big Bang, during the era known as recombination. Before recombination, the universe was a hot, dense plasma. Electrons and protons were free, making the universe opaque to light. As the universe cooled, electrons began to combine with protons to form neutral hydrogen atoms. This transition made the universe transparent to radiation. The release of the cosmic microwave background radiation marked the end of the hot plasma state. This radiation is a relic from the early universe and provides critical evidence for the Big Bang theory. With the formation of neutral atoms, gravity started to play a more prominent role. Matter began to clump together under the influence of gravitational forces. These clumps of matter eventually led to the formation of the first stars and galaxies. Over billions of years, these structures evolved into the complex cosmic web we see today. The cooling and expansion of the universe also influenced the behavior of dark matter and dark energy. Dark matter began to clump and form the scaffolding for galaxies, while dark energy drove the accelerated expansion of the universe. Observations of distant galaxies show that the universe is still expanding. This ongoing expansion means the universe continues to cool, albeit at a much slower rate. The rate of expansion is measured by the Hubble constant. Understanding this rate helps us learn more about the universe's age and its future trajectory. Instruments like the Hubble Space Telescope and the Planck satellite have provided detailed measurements of the universe's expansion and cooling. These observations refine our models of cosmic evolution. Cooling and expansion are fundamental to the universe's history. They set the stage for everything from the formation of the first atoms to the development of complex cosmic structures. One of the strongest pieces of evidence for the Big Bang and its subsequent stages is the cosmic microwave background radiation. This radiation is a faint glow left over from the early universe, providing a snapshot of the cosmos shortly after recombination. Measurements of the cosmic microwave background by satellites like COBE, WMAP, and Planck have confirmed its uniformity and slight fluctuations. These fluctuations correspond to the seeds of all future cosmic structures like galaxies and clusters. The abundance of light elements in the universe also supports the Big Bang model. Observations show the predicted ratios of hydrogen, helium, and lithium formed during nucleosynthesis in the first few minutes after the Big Bang. The redshift of galaxies provides further evidence. As the universe expands, light from distant galaxies stretches, shifting towards the red end of the spectrum. This redshift correlates with distance, confirming the expansion predicted by the Big Bang. Hubble's law quantifies this relationship between redshift and distance. Discovered by Edwin Hubble in the 1920s, it shows that galaxies are moving away from us, and the farther they are, the faster they move. Large-scale structure surveys map the distribution of galaxies across the universe. These maps reveal a web-like structure that aligns with predictions from the inflationary model, showing how initial fluctuations grew over time. Gravitational lensing, where massive objects bend light from background sources, also supports the Big Bang framework. Observations of lensing help measure the distribution of dark matter and confirm the large-scale structure's evolution. The observation of the accelerating expansion of the universe introduces another key piece of evidence. Discovered through studies of distant supernovae, this acceleration suggests the presence of dark energy driving the expansion. The distribution of galaxies and the cosmic web observed through surveys like the Sloan Digital Sky Survey align with theoretical models of the universe's growth from initial quantum fluctuations. This supports the stages predicted by the Big Bang. The cosmic infrared background provides information about the formation of the first stars and galaxies. Observations from instruments like the Spitzer Space Telescope help trace the light from these early objects, supporting theories about the universe's early stages. The consistency of these observations across different wavelengths and methods adds robustness to the Big Bang model. The agreement between theory and observation strengthens our understanding of the universe's history. Simulations of cosmic evolution, run on supercomputers, recreate the formation and growth of structures from the Big Bang to the present day. These simulations match observed data, validating the stages of cosmic evolution described by the Big Bang theory. High-energy particle experiments, such as those conducted at CERN, recreate conditions similar to those just after the Big Bang. These experiments help us understand the behavior of fundamental particles and forces in the early universe. Anisotropies in the cosmic microwave background, observed in fine detail by the Planck satellite, reveal information about the universe's composition, age, and development. These details match predictions from the Big Bang and inflationary models. Cosmologists continue to gather and refine evidence through observations and experiments. This ongoing research aims to answer remaining questions and further confirm the stages of the universe's evolution from the Big Bang onward. The discovery of the cosmic microwave background, or CMB, was a landmark moment in cosmology. It provided concrete evidence supporting the Big Bang theory. In 1964, Arno Penzias and Robert Wilson detected a persistent, faint microwave signal using a radio antenna. This signal was uniform in all directions and did not correspond to any known source. Initially, Penzias and Wilson were puzzled by this mysterious noise. They ruled out various sources, including radio interference and pigeon droppings in their antenna. At the same time, theoretical physicists Robert Dicke and Jim Peebles at Princeton University were predicting the existence of residual radiation from the Big Bang. Their calculations suggested that the early universe's hot plasma would leave behind a thermal radiation signature. Penzias and Wilson's findings matched these predictions perfectly. When they learned about the Princeton group's work, the significance of their discovery became clear. The cosmic microwave background is a remnant of the early universe, dating back to about 380,000 years after the Big Bang. It represents the moment when the universe cooled enough for atoms to form, making the universe transparent to radiation. This radiation is incredibly uniform, with tiny fluctuations that correspond to the seeds of future galaxies. These fluctuations are a crucial aspect of the inflationary model of the universe. The CMB is often referred to as the afterglow of the Big Bang. Its uniformity and spectrum are consistent with a hot, dense origin for the universe. The discovery of the CMB earned Penzias and Wilson the Nobel Prize in Physics in 1978. It transformed our understanding of the universe and solidified the Big Bang theory as the leading explanation for cosmic origins. Subsequent missions, like NASA's COBE satellite, have mapped the CMB in detail. COBE's measurements confirmed the CMB's blackbody spectrum and detected slight anisotropies. These anisotropies, or small temperature variations, provide a wealth of information about the early universe. They reveal the density fluctuations that led to the formation of galaxies and large-scale structures. The Wilkinson Microwave Anisotropy Probe, or WMAP, improved upon COBE's results. WMAP provided a detailed picture of the CMB, refining our understanding of the universe's age, composition, and development. The Planck satellite, launched by the European Space Agency, has provided the most precise measurements of the CMB to date. Planck's data has further confirmed the predictions of the Big Bang and inflationary models. Studying the CMB allows scientists to test hypotheses about the early universe and its subsequent evolution. It continues to be a vital tool in cosmological research. The discovery of the CMB marked a turning point in our understanding of the cosmos. It provided a direct link to the universe's origins and remains one of the most compelling pieces of evidence for the Big Bang theory. The cosmic microwave background, or CMB, is a cornerstone of modern cosmology. Its significance lies in the wealth of information it provides about the early universe. The CMB offers a direct glimpse into the universe when it was just 380,000 years old. This makes it an invaluable tool for understanding the conditions and processes of the early cosmos. Its uniformity across the sky supports the idea of a hot, dense origin for the universe. This uniformity is a key prediction of the Big Bang theory, which the CMB confirms. Tiny fluctuations in the CMB's temperature reveal the seeds of all current structures in the universe. These fluctuations correspond to regions of slightly different densities in the early universe. By studying these fluctuations, scientists can infer the distribution of matter and energy in the early universe. This helps us understand how galaxies, clusters, and other large-scale structures formed. The CMB also provides crucial data on the universe's age, composition, and rate of expansion. This data allows cosmologists to refine their models and improve our understanding of cosmic history. Observations of the CMB's anisotropies have led to the development of the lambda cold dark matter model, or lambda CDM. This model is the standard framework for explaining the universe's large-scale structure and evolution. The CMB's spectrum is a nearly perfect blackbody curve, indicating it originated from a state of thermal equilibrium. This matches the predictions of a universe that expanded and cooled from a hot, dense state. The polarization of the CMB gives us insights into the physics of the early universe, including the influence of primordial gravitational waves. These waves are ripples in spacetime generated by inflation. Measuring the CMB's polarization helps test theories of inflation and other aspects of high-energy physics. It provides a window into processes occurring fractions of a second after the Big Bang. The CMB's uniformity and the distribution of its fluctuations also support the theory of cosmic inflation. Inflation explains the rapid expansion of the universe and the uniformity we observe today. Detailed maps of the CMB, like those from the Planck satellite, reveal subtle patterns that inform us about the universe's geometry. These patterns confirm that the universe is flat on large scales, as predicted by inflation. The CMB is also essential for determining the Hubble constant, which measures the universe's expansion rate. Discrepancies in this value from different methods are an active area of research, highlighting the CMB's importance. The CMB acts as a cosmic time capsule, preserving information from the universe's infancy. Analyzing it allows scientists to test fundamental theories and explore the universe's deepest mysteries. Overall, the CMB's significance extends beyond just supporting the Big Bang theory. It continues to be a central piece of evidence in cosmological research, guiding our understanding of the universe's origins, structure, and fate. The cosmic microwave background has several key properties that make it invaluable for cosmological studies. Its uniformity and slight anisotropies provide a wealth of information about the early universe. One of its most important properties is its blackbody spectrum. This spectrum shows that the CMB has a nearly perfect thermal radiation curve, indicating it originated from a hot, dense state. The temperature of the CMB is approximately 2.725 Kelvin. This extremely cold temperature reflects the cooling of the universe over billions of years. Tiny fluctuations in this temperature, only about 1 part in 100,000, reveal critical details about the early universe. These anisotropies are crucial for understanding the distribution of matter and energy. The CMB is also polarized, meaning the light waves are oriented in specific directions. This polarization provides insights into the conditions of the early universe and the effects of primordial gravitational waves. Measurements of the CMB have been conducted by several key missions. The COBE satellite first detected its blackbody spectrum and anisotropies, revolutionizing our understanding of the universe. The WMAP satellite provided more detailed measurements, mapping the anisotropies with greater precision. WMAP's data refined our estimates of the universe's age, composition, and development. The Planck satellite has given us the most detailed map of the CMB to date. Planck's high-resolution measurements have provided a deeper understanding of the universe's early conditions and its large-scale structure. The CMB's properties are measured using specialized instruments that detect microwave radiation. These instruments are capable of extremely sensitive measurements, detecting minute temperature variations across the sky. Detailed maps of the CMB reveal a pattern of hot and cold spots. These spots correspond to regions of slightly higher and lower densities in the early universe, leading to the formation of galaxies and clusters. Analyzing the CMB's power spectrum allows scientists to extract important cosmological parameters. This includes the density of different types of matter and energy, the Hubble constant, and the curvature of the universe. The polarization of the CMB is measured in terms of E modes and B modes. E modes are generated by density fluctuations, while B modes can be produced by gravitational waves, offering insights into the universe's inflationary period. The CMB's isotropy, or uniformity, and its tiny anisotropies are key to testing cosmological models. The detailed measurements align with predictions of the Big Bang and inflationary theories. The precision of these measurements continues to improve with advancements in technology and observational techniques. Each new set of data helps refine our understanding of the universe's earliest moments. Understanding the properties and measurements of the CMB is essential for piecing together the history of the universe. It provides a direct link to the conditions that shaped everything we observe today. The cosmic microwave background, or CMB, provides a snapshot of the universe at a very young age. This snapshot is crucial for understanding how the large-scale structure of the universe formed. The tiny fluctuations in the CMB are the seeds of all current cosmic structures. These fluctuations represent slight variations in density that grew over time due to gravitational attraction. As the universe expanded and cooled, regions with higher density attracted more matter. This process eventually led to the formation of galaxies, clusters, and superclusters. By studying the pattern of these fluctuations, scientists can trace the evolution of cosmic structures. The detailed maps of the CMB show how matter was distributed in the early universe. The CMB also reveals information about dark matter. Dark matter does not emit light, but its gravitational effects influence the formation of structures in the universe. The pattern of CMB fluctuations helps scientists understand the distribution and amount of dark matter. This, in turn, informs models of how galaxies and other structures formed and evolved. The large-scale structure of the universe, often described as a cosmic web, can be traced back to these early fluctuations. The web-like pattern of galaxies and clusters corresponds to the initial density variations seen in the CMB. The CMB also provides clues about the role of dark energy. Dark energy drives the accelerated expansion of the universe, influencing the growth of structures over time. The alignment and distribution of the CMB's fluctuations give insights into the geometry of the universe. Observations indicate that the universe is flat, which has implications for its overall structure and fate. Gravitational lensing of the CMB, where light is bent by massive objects, offers another way to study the universe's structure. This lensing effect helps map the distribution of matter, both visible and dark. The detailed study of the CMB has led to the development of the lambda cold dark matter model. This model describes the universe's composition and structure, including the roles of dark matter and dark energy. The CMB's data helps refine simulations of cosmic evolution. These simulations recreate the formation and growth of structures from the Big Bang to the present day, matching the observed distribution of galaxies and clusters. Understanding the CMB and its connection to the universe's structure allows scientists to test fundamental theories of cosmology. This includes theories about inflation, dark matter, and dark energy. The CMB remains a critical tool for probing the universe's earliest moments and its subsequent development. Its detailed study continues to reveal new insights about the origins and evolution of cosmic structures. As technology advances, future observations of the CMB will provide even more detailed information. This ongoing research will help answer remaining questions about the universe's structure and the fundamental forces that shaped it. The cosmic microwave background, or CMB, is one of the most compelling pieces of evidence supporting the Big Bang theory. Its existence and properties align perfectly with the predictions of this model. The uniform temperature of the CMB across the sky suggests that the universe began from a hot, dense state. This uniformity supports the idea that the early universe was in thermal equilibrium. The CMB's blackbody spectrum indicates it originated from a time when the universe was hot and opaque. This matches the Big Bang model's description of the universe's early conditions. Tiny temperature fluctuations in the CMB provide insights into the density variations in the early universe. These fluctuations are consistent with the initial conditions predicted by the Big Bang. The distribution and size of these fluctuations fit the theoretical models of cosmic inflation. Inflation explains the rapid expansion that smoothed out any irregularities and set the stage for the universe's large-scale structure. The discovery of the CMB was predicted by the Big Bang theory before it was observed. This prediction and its subsequent confirmation is a significant validation of the theory. The abundance of light elements observed in the universe matches the predictions of Big Bang nucleosynthesis. The CMB provides a backdrop that helps verify these predictions. The CMB's detailed measurements help determine the Hubble constant, which describes the rate of the universe's expansion. This expansion is a key component of the Big Bang theory. The polarization patterns in the CMB offer additional support. These patterns match the theoretical predictions of how light would scatter off particles in the early universe. Gravitational lensing of the CMB helps map the distribution of dark matter. This mapping aligns with the predictions of the Big Bang model concerning the formation of cosmic structures. The age of the universe determined from the CMB is consistent with other independent measurements. This consistency reinforces the Big Bang theory's timeline. The CMB's properties also support the concept of a flat universe. This flatness is a direct prediction of the inflationary Big Bang model, confirmed by CMB observations. The power spectrum of the CMB, which shows the strength of fluctuations at different scales, matches theoretical predictions. This spectrum provides a detailed fingerprint of the early universe. By studying the CMB, scientists can test and refine models of the universe's evolution. The CMB's data continuously supports the framework established by the Big Bang theory. The CMB remains a cornerstone of observational cosmology, providing a critical link between theory and observation. Its study continues to affirm the Big Bang as the leading explanation for the origin and development of the universe. Baryogenesis is the process that explains the imbalance between matter and antimatter in the universe. This imbalance is crucial for the existence of the matter that makes up stars, planets, and life itself. In the early universe, matter and antimatter were created in almost equal amounts. When matter and antimatter meet, they annihilate each other, leaving behind pure energy. However, for reasons not fully understood, a slight excess of matter over antimatter was produced during baryogenesis. This tiny asymmetry allowed matter to dominate the universe after most of the antimatter was annihilated. One of the key conditions for baryogenesis is the violation of certain symmetries in physics. These symmetries include charge conjugation, C, parity P, and time reversal, T. The combined violation of charge and parity symmetry, known as CP violation, is essential for creating a matter-antimatter imbalance. CP violation has been observed in certain particle interactions, providing a clue about how baryogenesis might have occurred. The standard model of particle physics includes some sources of CP violation, but not enough to account for the observed matter-antimatter asymmetry. This suggests new physics beyond the standard model is needed to fully explain baryogenesis. Theories such as supersymmetry and leptogenesis propose mechanisms for baryogenesis. These theories extend the standard model and provide additional sources of CP violation and other necessary conditions. Experiments at particle accelerators like those at CERN are designed to explore these theories. By studying high-energy particle collisions, scientists hope to uncover evidence of the processes involved in baryogenesis. The conditions in the early universe were extreme, with temperatures and energies far beyond those achievable in laboratories. Understanding baryogenesis requires recreating and studying these conditions as closely as possible. Observations of the cosmic microwave background and the distribution of elements in the universe provide indirect evidence for baryogenesis. These observations align with the predicted outcomes of a universe where baryogenesis occurred. Baryogenesis also has implications for the nature of dark matter. Some theories suggest that dark matter particles could be related to the processes that created the matter-antimatter imbalance. Understanding baryogenesis is crucial for a complete picture of the universe's evolution. It links the fundamental forces and particles with the large-scale structure and composition of the cosmos. The study of baryogenesis is an active and exciting field in theoretical and experimental physics. Discoveries in this area could provide profound insights into the fundamental nature of matter and the early universe. By solving the mystery of baryogenesis, scientists hope to answer one of the most fundamental questions in cosmology. This research could reveal why the universe exists in its current form, dominated by matter. As we continue to investigate baryogenesis, we deepen our understanding of the universe's origin and the fundamental laws that govern it. This journey brings us closer to comprehending the full story of our cosmic beginnings. The formation of protons and neutrons occurred within the first few minutes of the universe. This period is known as the epoch of nucleosynthesis. During this time, the universe was extremely hot and dense. Conditions were similar to those found in the core of a star, but on a much larger scale. Protons and neutrons are composed of quarks, held together by the strong nuclear force. This force is mediated by particles called gluons. In the early universe, quarks and gluons were in a state known as quark-gluon plasma. As the universe cooled, quarks began to combine to form protons and neutrons. A proton consists of 2 up quarks and 1 down quark. Neutrons, on the other hand, are made up of 2 down quarks and 1 up quark. The balance between protons and neutrons was initially governed by the weak nuclear force. This force allows for the transformation of protons into neutrons and vice versa. As the universe continued to expand and cool, the rates of these transformations slowed down. Eventually, protons and neutrons were no longer able to change into each other easily. The slight excess of protons over neutrons was crucial for the formation of hydrogen, the most abundant element in the universe. Neutrons, being slightly heavier than protons, tend to decay into protons over time. This process of neutron decay is why free neutrons are relatively rare in the universe today. Most neutrons are found within atomic nuclei, where they are stable. The formation of protons and neutrons set the stage for the creation of atomic nuclei. These nuclei would later combine with electrons to form neutral atoms. The abundance of protons compared to neutrons led to the predominance of hydrogen. Helium and trace amounts of other light elements were also formed during this period. Understanding the formation of protons and neutrons helps explain the universe's elemental composition. These particles are the building blocks of all matter. Experiments with particle accelerators allow scientists to study conditions similar to those of the early universe. These experiments help us understand the behavior of quarks and gluons. The study of protons and neutrons is fundamental to nuclear physics and cosmology. It provides insights into the forces and particles that shaped the early universe. As we continue to explore these fundamental particles, we gain a deeper understanding of the universe's origin and evolution. This knowledge is crucial for piecing together the history of the cosmos. Nucleosynthesis refers to the process of creating new atomic nuclei from pre-existing nucleons, primarily protons and neutrons. This process occurred during the first few minutes after the Big Bang. The most significant period of nucleosynthesis is known as Big Bang nucleosynthesis. During this time, the universe was hot and dense enough for nuclear reactions to occur. Big Bang nucleosynthesis led to the formation of the lightest elements in the universe. These elements include hydrogen, helium, and trace amounts of lithium and beryllium. Hydrogen formed the majority of the universe's elemental composition. About 75% of the universe's baryonic mass was converted into hydrogen nuclei, or protons. Helium was the second most abundant element formed during nucleosynthesis. About 25% of the universe's baryonic mass was converted into helium nuclei, or alpha particles. The formation of helium required a sequence of nuclear reactions. Protons and neutrons combined to form deuterium, which then fused to create helium. Deuterium, or heavy hydrogen, is an isotope of hydrogen with 1 proton and 1 neutron. Its abundance provides a crucial test for models of the early universe. Lithium and beryllium were produced in much smaller quantities. These elements formed through interactions involving helium and deuterium nuclei. The precise ratios of these light elements offer important clues about the conditions of the early universe. Observations of these ratios match predictions made by the Big Bang theory. Nucleosynthesis ceased once the universe expanded and cooled to the point where nuclear reactions could no longer occur. This happened within the first few minutes after the Big Bang. The elements formed during nucleosynthesis became the building blocks for later cosmic structures. Stars and galaxies formed from clouds of these primordial elements. Studying the abundance of light elements helps cosmologists understand the density and expansion rate of the early universe. These measurements provide strong evidence for the Big Bang theory. Observations of ancient stars and gas clouds allow scientists to measure the abundance of these primordial elements. These observations are consistent with theoretical predictions. The process of nucleosynthesis continues in stars today. Stellar nucleosynthesis creates heavier elements, building on the foundation laid during the Big Bang. Understanding nucleosynthesis and the formation of light elements is crucial for piecing together the history of the cosmos. It reveals how the universe transitioned from a hot, dense state to the rich structure we observe today. One of the greatest mysteries in cosmology is the asymmetry between matter and antimatter. In the early universe, matter and antimatter were created in almost equal amounts. When matter and antimatter meet, they annihilate each other, producing energy. However, the observable universe is dominated by matter, with very little antimatter present. This imbalance suggests that a slight excess of matter was produced in the early universe. This excess allowed some matter to survive after most of the antimatter was annihilated. The process that led to this asymmetry is known as baryogenesis. Baryogenesis requires certain conditions, such as CP violation, to create more matter than antimatter. CP violation refers to a difference in the behavior of particles and their antiparticles. This violation has been observed in certain particle interactions, but is not fully understood. The standard model of particle physics includes some sources of CP violation. However, these sources are not sufficient to explain the observed matter-antimatter asymmetry. This suggests that new physics beyond the standard model is needed to fully explain the asymmetry. Theories such as leptogenesis propose additional mechanisms for creating the imbalance. Leptogenesis involves the creation of an excess of leptons, such as electrons, over antileptons. This excess can be converted into an excess of baryons, such as protons, over antibaryons. Experiments at particle accelerators, like those at CERN, aim to study CP violation in detail. These experiments may uncover new sources of CP violation that could explain the asymmetry. Observations of the cosmic microwave background and the distribution of elements in the universe provide indirect evidence for matter-antimatter asymmetry. These observations align with the predicted outcomes of a universe where baryogenesis occurred. Understanding the matter-antimatter asymmetry is crucial for a complete picture of the universe's evolution. It links the fundamental forces and particles with the large-scale structure and composition of the cosmos. The study of this asymmetry is an active and exciting field in theoretical and experimental physics. Discoveries in this area could provide profound insights into the fundamental nature of matter and the early universe. By solving the mystery of matter-antimatter asymmetry, scientists hope to answer one of the most fundamental questions in cosmology. This research could reveal why the universe exists in its current form, dominated by matter. As we continue to investigate this asymmetry, we deepen our understanding of the universe's origin and the fundamental laws that govern it. This journey brings us closer to comprehending the full story of our cosmic beginnings. The matter-antimatter asymmetry remains one of the most intriguing and challenging problems in modern physics. Solving it will provide crucial insights into the nature of the universe and the fundamental forces that shape it. Quarks and leptons are the fundamental building blocks of matter. They play a crucial role in the composition and behavior of the universe. Quarks combine to form protons and neutrons, which make up the nuclei of atoms. There are 6 types of quarks, known as flavors: up, down, charm, strange, top, and bottom. Protons are composed of 2 up quarks and 1 down quark. Neutrons consist of 2 down quarks and 1 up quark. Leptons are another family of fundamental particles. The most familiar lepton is the electron, which orbits the nucleus of an atom. There are 6 types of leptons, divided into 3 pairs: the electron and the electron neutrino, the muon and the muon neutrino, and the tau and the tau neutrino. Quarks and leptons interact through fundamental forces mediated by exchange particles. The strong force, carried by gluons, binds quarks together inside protons and neutrons. The electromagnetic force, mediated by photons, affects charged leptons like electrons. The weak force, carried by W and Z bosons, is responsible for processes like beta decay in nuclear reactions. The behavior of quarks and leptons is described by the standard model of particle physics. This model provides a framework for understanding how these particles interact and combine to form matter. Experiments with particle accelerators, such as those at CERN, allow scientists to study quarks and leptons in detail. These experiments recreate high-energy conditions similar to those of the early universe. Quarks and leptons were among the first particles to form after the Big Bang. As the universe cooled, they combined to create the first protons and neutrons. The interactions of quarks and leptons also play a role in the matter-antimatter asymmetry. CP violation in the interactions of these particles may have contributed to the excess of matter over antimatter. Neutrinos, a type of lepton, are particularly intriguing. They are incredibly light and interact very weakly with other matter, making them difficult to detect. Neutrino oscillations, where a neutrino changes from one type to another, provide evidence for physics beyond the standard model. These oscillations are key to understanding the full role of leptons in the universe. The study of quarks and leptons helps scientists probe the fundamental structure of matter. It also provides insights into the forces that governed the early universe and continue to shape its evolution. Understanding quarks and leptons is essential for a complete picture of particle physics and cosmology. Their role is central to the formation of all known matter and the dynamics of the universe. The universe has evolved through several key epochs, each marked by significant events and transitions. These epochs trace the history from the Big Bang to the present day. The Planck epoch was the earliest stage, lasting until 10 hours and 43 seconds after the Big Bang. During this time, the four fundamental forces were unified. Next came the Grand Unification epoch, which lasted until 10 hours to 36 seconds after the Big Bang. Here, gravity separated from the other three forces. The inflationary epoch followed, where the universe expanded exponentially in a fraction of a second. This rapid expansion smoothed out any irregularities. After inflation, the universe entered the electro-weak epoch. Lasting until 10 and 12 seconds after the Big Bang, the electromagnetic and weak forces separated. The quark epoch came next, where the universe was filled with a hot, dense plasma of quarks and gluons. This epoch lasted until 10 and 6 seconds after the Big Bang. During the hadron epoch, quarks combined to form protons and neutrons. This epoch lasted from 10 and 6 seconds to 1 second after the Big Bang. The lepton epoch followed, where leptons dominated the universe. This period lasted until about 10 seconds after the Big Bang. Next was the photon epoch, where photons dominated the universe's energy. This epoch lasted until about 380,000 years after the Big Bang, leading to the formation of neutral atoms. The Dark Ages began after recombination, lasting until the first stars formed. During this time, the universe was dark and filled with neutral hydrogen. The ionization epoch followed, where the first stars and galaxies formed and ionized the surrounding hydrogen. This epoch lasted from around 150 million to 1 billion years after the Big Bang. The stellar epoch, spanning from the formation of the first stars to the present, is characterized by the ongoing formation and evolution of stars and galaxies. The universe's expansion rate has changed over time. The deceleration epoch saw gravity slowing the expansion until dark energy began to dominate. The current epoch, dominated by dark energy, is known as the accelerating epoch. This phase sees the universe's expansion rate increasing. Understanding these epochs helps scientists trace the universe's evolution. Each epoch reveals critical insights into the processes that shape the cosmos. The study of the universe's epochs continues to provide valuable information about its history and future. This ongoing research enhances our understanding of the fundamental nature of the universe. The formation of the first atoms marked a significant milestone in the early universe. This period is known as the epoch of recombination. During recombination, the universe cooled enough for protons and electrons to combine and form neutral hydrogen atoms. This occurred about 380,000 years after the Big Bang. Before recombination, the universe was a hot, dense plasma of charged particles. Photons constantly scattered off electrons, making the universe opaque. As the universe cooled, electrons and protons could combine without being immediately ionized by high-energy photons. This allowed for the formation of stable, neutral atoms. The formation of neutral atoms led to the decoupling of matter and radiation. Photons could now travel freely through space, leading to the release of the cosmic microwave background radiation. The cosmic microwave background provides a snapshot of the universe at the moment of recombination. It shows a remarkably uniform temperature with slight fluctuations. These fluctuations in the cosmic microwave background are the seeds of all future structure in the universe. They represent regions of slightly different densities that would later form galaxies and clusters. Recombination also marked the beginning of the universe's transparent phase. For the first time, light could travel long distances without being scattered by free electrons. This transition from an opaque to a transparent universe had profound implications. It allowed the universe to cool further and set the stage for the formation of larger structures. The cooling continued as the universe expanded, leading to the gradual accumulation of neutral hydrogen gas. This gas would eventually collapse under gravity to form the first stars and galaxies. The study of recombination and the formation of the first atoms provides crucial insights into the early universe. It helps us understand the conditions that led to the formation of cosmic structures. Recombination is also important for cosmological models. Accurate models of this period are essential for interpreting the cosmic microwave background and other observations. Observations of the cosmic microwave background by missions like Planck and WMAP have provided detailed data on recombination. These observations confirm the predictions of the Big Bang theory. Understanding recombination and the formation of the first atoms is a key part of cosmology. It connects the early universe's high-energy physics with the formation of the first stars and galaxies. This period set the stage for everything that followed, from the formation of galaxies to the development of life. It is a fundamental chapter in the history of the universe. The development of large-scale structures began shortly after the formation of the first atoms. Gravity started to amplify the slight density fluctuations present in the early universe. These density fluctuations were the seeds from which galaxies, clusters, and superclusters would grow. Over time, regions of higher density began to attract more matter. As matter clumped together under the influence of gravity, the first stars and galaxies started to form. This process took hundreds of millions of years. The first galaxies were small and irregular, gradually merging to form larger structures. These mergers played a crucial role in shaping the universe's large-scale structure. Dark matter also played a significant role in the development of these structures. Its gravitational effects helped pull ordinary matter into clumps, forming the scaffolding for galaxies and clusters. Observations of the cosmic microwave background show the initial conditions that led to these structures. The patterns of temperature fluctuations correspond to the early density variations. As galaxies formed, they began to cluster together under gravity. These clusters are the largest gravitationally bound structures in the universe. Superclusters, which are collections of galaxy clusters, formed on even larger scales. They represent the largest coherent structures in the universe. The large-scale structure of the universe is often described as a cosmic web. This web consists of filaments of galaxies separated by vast voids. The formation of this cosmic web is a result of the interplay between gravity and the initial density fluctuations. Over billions of years, the universe evolved into the complex structure we observe today. Studying the distribution of galaxies helps scientists understand the processes that shape the universe. Large-scale surveys like the Sloan Digital Sky Survey map the positions of millions of galaxies. These surveys reveal the intricate patterns of the cosmic web and provide insights into the universe's composition and evolution. They also help test cosmological models. Simulations of cosmic evolution use these observations to recreate the growth of large-scale structures. These simulations match the observed distribution of galaxies, validating our understanding of cosmic history. Understanding the development of large-scale structures connects the physics of the early universe with the complex structures we see today. It reveals how the universe transitioned from a nearly uniform state to one filled with galaxies and clusters. This ongoing research continues to provide valuable information about the universe's evolution. It enhances our knowledge of the fundamental processes that govern cosmic structure formation. After the formation of the first atoms, the universe entered a period known as the Dark Ages. During this time, there were no stars or galaxies to light up the cosmos. The Dark Ages lasted until the first stars and galaxies began to form. This period is crucial for understanding the transition from a simple to a complex universe. During the Dark Ages, the universe was filled with neutral hydrogen gas. This gas absorbed any photons, preventing light from traveling long distances. Gravity continued to pull matter into denser regions, eventually leading to the formation of the first stars. These stars were massive and short-lived, ending their lives in supernova explosions. The light from these first stars began to ionize the surrounding hydrogen gas. This process marked the end of the Dark Ages and the beginning of the epoch of ionization. Ionization was a gradual process that took hundreds of millions of years. It transformed the universe from an opaque state to one where light could travel freely. The first galaxies also contributed to reionization. Their intense radiation ionized the gas in their vicinity, creating bubbles of ionized hydrogen. As more stars and galaxies formed, these bubbles grew and eventually overlapped. This led to a universe filled with ionized gas, similar to the state we observe today. Reionization is a critical phase in cosmic history. It allowed the universe to become transparent to ultraviolet light, enabling us to see distant objects. Observations of distant quasars provide evidence for reionization. The light from these quasars shows signatures of interaction with the ionized gas. The cosmic microwave background also carries imprints of the reionization process. Subtle features in the CMB provide clues about the timing and duration of reionization. Understanding reionization helps scientists learn about the formation of the first stars and galaxies. It connects the early universe's physics with the large-scale structure we see today. Simulations of reionization help researchers explore how this process unfolded. These simulations match observations, confirming our understanding of this critical epoch. The study of reionization continues to be a vibrant field of research. New observations and advanced simulations are providing deeper insights into this transformative period. Reionization marks the end of the Dark Ages and the beginning of the universe as we know it. It set the stage for the complex cosmic structures that developed in the following billions of years. Following the epoch of reionization, the universe continued to evolve into the complex cosmos we observe today. Stars and galaxies formed and clustered together under the influence of gravity. The first galaxies were small and irregular, gradually merging to form larger galaxies. These mergers played a crucial role in the growth and evolution of galaxies. Over billions of years, galaxies began to take on the shapes we see today, such as spiral and elliptical forms. These structures were influenced by the interactions and mergers of smaller galaxies. Galactic evolution was also driven by the formation of new stars. Star formation occurred in bursts, often triggered by galactic collisions and interactions. The formation of stars also led to the creation of heavier elements through nuclear fusion. These elements were dispersed into space by supernova explosions, enriching the interstellar medium. As galaxies grew and evolved, they began to form large clusters and superclusters. These structures are the largest gravitationally bound systems in the universe. Dark matter played a significant role in the formation of these large-scale structures. Its gravitational effects helped bind galaxies together into clusters. Observations of distant galaxies and clusters provide a window into the past, showing us how the universe has evolved over time. These observations are made using powerful telescopes that capture light from billions of years ago. The expansion of the universe has continued since the Big Bang, but at an accelerating rate due to dark energy. This accelerated expansion affects the growth and distribution of cosmic structures. The cosmic web, a vast network of galaxies and clusters connected by filaments of dark matter, represents the large-scale structure of the universe. This web-like pattern formed over billions of years through the interplay of gravity and expansion. Our own galaxy, the Milky Way, is part of this cosmic web. It formed from the merging of smaller galaxies and continues to evolve through interactions with nearby galaxies. The solar system, including Earth, formed about 4.6 billion years ago from a cloud of gas and dust within the Milky Way. The formation of our solar system was part of the broader process of galactic evolution. Understanding the progression to the present-day universe involves studying a wide range of cosmic phenomena. From the life cycles of stars to the dynamics of galaxies, each piece of the puzzle contributes to our overall understanding. Advanced simulations and observations continue to refine our models of cosmic evolution. These tools help scientists test theories and uncover new aspects of the universe's history. The journey from the Big Bang to the present day is a story of continuous change and growth. Each epoch and event has shaped the universe into the complex and dynamic system we observe now. Hubble's law is a fundamental principle in cosmology that describes the expansion of the universe. Discovered by Edwin Hubble in the 1920s, it provides evidence for the Big Bang theory. Hubble observed that distant galaxies are moving away from us. He found that the farther a galaxy is, the faster it is receding. This relationship between distance and velocity is described by Hubble's law. The law is expressed with the formula v Matter-antimatter, where v is the galaxy's velocity, h0 is the Hubble constant, and d is the distance to the galaxy. The Hubble constant represents the rate of expansion of the universe. Determining its precise value has been a major focus of astronomical research. Hubble's discovery was revolutionary because it showed that the universe is dynamic, not static. It provided strong evidence that the universe began with a rapid expansion, as described by the Big Bang theory. By measuring the redshift of light from distant galaxies, astronomers can determine their velocities. Redshift occurs because the wavelength of light stretches as the galaxy moves away, shifting it towards the red end of the spectrum. Hubble's law implies that the universe is expanding uniformly. This expansion means that space itself is stretching, causing galaxies to move apart. The discovery of cosmic expansion led to the concept of the observable universe. This is the region of the universe we can see, limited by the speed of light and the age of the universe. Hubble's law has been refined with more precise measurements. Observations from telescopes like the Hubble Space Telescope have provided detailed data on galaxy distances and velocities. The value of the Hubble constant has been a subject of debate. Different methods, such as observing Cepheid variables or the cosmic microwave background, have produced slightly different values. Understanding the Hubble constant is crucial for determining the age and size of the universe. It also has implications for the ultimate fate of the universe. Hubble's law supports the idea that the universe has no center or edge. Every point in the universe appears to be moving away from every other point, consistent with an expanding space. The expansion rate of the universe has changed over time. Observations indicate that the expansion is currently accelerating, driven by a mysterious force called dark energy. Hubble's law continues to be a fundamental tool in cosmology. It helps scientists explore the large-scale structure of the universe and understand its evolution. The study of cosmic expansion and Hubble's law reveals the dynamic nature of the universe. It connects the motions of galaxies with the overall history and structure of the cosmos. Redshift is a phenomenon observed in the light from distant galaxies. It occurs when the wavelength of light is stretched, shifting it towards the red end of the spectrum. This stretching of light is a direct result of the expansion of the universe. As galaxies move away from us, the space between us stretches, causing the light to redshift. The Doppler effect is a similar phenomenon that occurs with sound waves. It explains how the pitch of a sound changes as the source moves relative to the observer. In the case of light, the Doppler effect describes how the frequency and wavelength of light change due to the relative motion of the source and observer. For galaxies moving away, this results in a redshift. Redshift provides crucial information about the velocity and distance of galaxies. By measuring the amount of redshift, astronomers can determine how fast a galaxy is receding from us. The greater the redshift, the faster the galaxy is moving away. This relationship is a key component of Hubble's law and helps measure the expansion rate of the universe. There are different types of redshift: cosmological, gravitational, and Doppler redshift. Cosmological redshift is caused by the expansion of the universe, while Doppler redshift is due to the relative motion of objects. Gravitational redshift occurs when light escapes from a strong gravitational field. The light loses energy and its wavelength increases, shifting it to the red end of the spectrum. Cosmological redshift is the most significant in understanding the universe's expansion. It provides evidence that the universe has been expanding since the Big Bang. Observations of redshift in distant galaxies support the idea that the universe is not static. Instead, it is continuously expanding, with galaxies moving away from each other over time. The study of redshift also helps map the large-scale structure of the universe. By measuring redshifts, astronomers can create three-dimensional maps of galaxy distributions. These maps reveal the web-like structure of the universe, with galaxies and clusters connected by filaments of dark matter. Redshift surveys are essential for understanding the distribution of matter on a cosmic scale. Redshift measurements are used to estimate the age of the universe. By understanding how the universe's expansion rate has changed over time, scientists can infer its overall age. The concept of redshift is fundamental to cosmology. It links observations of distant galaxies with the theoretical framework of the expanding universe. Understanding redshift and the Doppler effect allows astronomers to explore the dynamics of the cosmos. These concepts are essential for unraveling the history and evolution of the universe. Measuring the expansion rate of the universe is critical for understanding its history and future. This rate is quantified by the Hubble constant, which indicates how fast galaxies are receding from us. There are several methods to measure the Hubble constant. One common approach is observing Cepheid variable stars, which have a known relationship between their luminosity and pulsation period. By measuring the apparent brightness of Cepheids in distant galaxies, astronomers can determine their distance. Comparing these distances with the redshifts of their host galaxies helps calculate the Hubble constant. Another method involves observing Type Ia supernovae. These stellar explosions have a consistent peak brightness, making them reliable standard candles for measuring cosmic distances. The cosmic microwave background also provides a way to measure the expansion rate. Observations from satellites like WMAP and Planck give precise data on the early universe's conditions, helping to estimate the Hubble constant. Gravitational lensing offers another technique. By studying how light from distant objects is bent by massive foreground galaxies, scientists can infer distances and expansion rates. Each method of measuring the Hubble constant has its advantages and challenges. Combining results from different techniques provides a more accurate and comprehensive understanding. The Hubble constant has been a subject of intense research and debate. Different measurement methods have yielded slightly varying values, leading to the so-called Hubble tension. Understanding this discrepancy is a major goal in modern cosmology. Resolving the Hubble tension may require new physics or revisions to our current models of the universe. Measuring the expansion rate also informs us about the nature of dark energy. This mysterious force drives the accelerated expansion of the universe, influencing the value of the Hubble constant. The expansion rate affects the estimated age of the universe. A precise Hubble constant helps refine calculations of how long the universe has been expanding since the Big Bang. Advanced telescopes and observatories continue to improve our measurements. Instruments like the Hubble Space Telescope and the upcoming James Webb Space Telescope provide detailed data on distant objects. Understanding the expansion rate is crucial for predicting the universe's future. Whether it will continue to expand indefinitely, slow down, or eventually collapse depends on the precise measurement of this rate. The study of cosmic expansion connects observations of distant galaxies with fundamental questions about the universe's origin, structure, and fate. It remains a central focus of astronomical research. As technology advances, our ability to measure the expansion rate becomes more precise. These improvements will help address current challenges and deepen our understanding of the cosmos. The discovery of the universe's accelerating expansion was a groundbreaking revelation. It suggested that the cosmos is not just expanding, but doing so at an increasing rate. This acceleration was first observed in the late 1990s by two independent research teams. They studied distant Type Ia supernovae and found that these supernovae were dimmer than expected, indicating that they were farther away than previously thought. The cause of this accelerating expansion is attributed to a mysterious force known as dark energy. Dark energy is thought to make up about 70% of the total energy content of the universe. Dark energy counteracts the gravitational pull of matter, driving the accelerated expansion. Its exact nature remains one of the biggest mysteries in modern physics. Observations of the cosmic microwave background support the existence of dark energy. Data from the WMAP and Planck satellites show patterns that align with an accelerating universe. The effects of dark energy become more significant over time. In the early universe, matter dominated, but as the universe expanded, dark energy's influence grew stronger. Measuring the rate of acceleration helps cosmologists understand the properties of dark energy. This includes its density and how it affects the universe's expansion over time. The concept of a cosmological constant, first introduced by Einstein, is one possible explanation for dark energy. The cosmological constant represents a constant energy density filling space uniformly. Another theory involves dynamic forms of dark energy, such as quintessence. Unlike the cosmological constant, quintessence suggests that dark energy density can change over time. The accelerating expansion has profound implications for the universe's fate. If the expansion continues to accelerate, galaxies will move farther apart. eventually becoming isolated in a dark, cold universe. This scenario, known as the Big Freeze or heat death, predicts a universe where star formation ceases and galaxies fade away. Over trillions of years, only remnants of stars and black holes will remain. The study of accelerating expansion also involves large-scale surveys of galaxies and clusters. Projects like the Sloan Digital Sky Survey map the distribution of galaxies to understand how dark energy influences structure formation. Advanced telescopes and instruments continue to improve our understanding of accelerating expansion. Future missions, such as the European Space Agency's Euclid satellite, aim to probe dark energy with unprecedented precision. Understanding the accelerating expansion is crucial for a complete picture of cosmology. It connects the past evolution of the universe with its future trajectory, revealing the fundamental forces shaping our cosmos. As research progresses, we hope to uncover the true nature of dark energy and its role in the universe's destiny. This knowledge will transform our understanding of the fundamental workings of the universe. The accelerating expansion of the universe has profound implications for its future. One possible scenario is the Big Freeze, where the universe continues to expand indefinitely. In the Big Freeze, galaxies will move farther apart, making it increasingly difficult for stars to form. Over billions of years, existing stars will burn out, leaving a dark and cold universe. Another possibility is the Big Rip, where the acceleration increases to the point that it tears apart galaxies, stars, and even atoms. This scenario depends on the nature of dark energy. If dark energy becomes stronger over time, it could lead to the Big Rip. The universe would be torn apart, ending in a dramatic and violent event. A less extreme scenario is the Big Crunch, where the expansion eventually reverses, and the universe collapses back into a hot, dense state. This would occur if dark energy decreases, or if gravity overcomes the expansion. In the Big Crunch, all matter would be pulled back into a single point, possibly leading to another Big Bang. This cyclical model suggests a repeating universe. Current observations favor the Big Freeze or Big Rip scenarios due to the evidence of accelerating expansion. However, the exact fate of the universe remains uncertain. Understanding the future of the universe requires precise measurements of the Hubble constant and the properties of dark energy. These measurements help refine our models of cosmic evolution. The implications for galaxies are significant. In an accelerating universe, galaxies will drift apart, eventually becoming isolated from each other. For our own Milky Way, this means future interactions with neighboring galaxies like Andromeda will shape its evolution. However, over time, it will become increasingly isolated. Star formation will eventually cease as galaxies exhaust their gas supplies. The universe will enter an era dominated by black holes and dark matter. The distant future of the universe will see the slow decay of black holes through Hawking radiation. This process will take an unimaginably long time. The study of cosmic acceleration also impacts our understanding of fundamental physics. It raises questions about the nature of energy, space, and time. The search for a deeper understanding of dark energy is one of the most exciting areas in cosmology. Solving this mystery could revolutionize our understanding of the universe. The implications for the future of the universe are both fascinating and humbling. They remind us of the dynamic and ever-changing nature of the cosmos. Dark matter is a mysterious and invisible form of matter that makes up about 27% of the universe's total mass and energy. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, making it invisible to current telescopes. Despite being invisible, dark matter exerts a gravitational influence on visible matter. This gravitational pull affects the motion of galaxies and galaxy clusters, providing indirect evidence of its existence. One of the key pieces of evidence for dark matter comes from observing the rotation curves of galaxies. Stars at the edges of galaxies rotate faster than can be explained by the visible mass alone, suggesting the presence of an unseen mass. Gravitational lensing is another method that reveals the presence of dark matter. When light from distant objects passes near massive galaxy clusters, it is bent, indicating more mass than is visible. Dark matter is thought to be composed of unknown particles that interact weakly with normal matter. These particles are referred to as weakly interacting massive particles, or WIMPs. The nature of dark matter particles remains one of the biggest mysteries in physics. Various experiments are underway to detect these particles directly or indirectly. Dark matter does not interact with electromagnetic forces, which is why it does not emit or absorb light. This property makes it difficult to detect using traditional astronomical methods. Its presence is inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Dark matter plays a crucial role in the formation and evolution of galaxies. Without dark matter, galaxies would not have enough mass to hold together under their own gravity. It acts as a gravitational glue, binding galaxies and galaxy clusters. Dark matter also influences the cosmic microwave background. Its gravitational effects create subtle imprints in the CMB that help cosmologists understand the early universe. The distribution of dark matter in the universe is mapped through observations of galaxy clustering and gravitational lensing. These maps show a web-like structure, with dark matter forming the backbone of cosmic structure. There are several candidates for dark matter particles, including axions and sterile neutrinos. These hypothetical particles are being studied through various detection methods. The search for dark matter involves experiments deep underground, in space, and in particle accelerators. Each approach aims to uncover the elusive particles that make up dark matter. Understanding dark matter is essential for a complete picture of the universe. It connects the smallest particles to the largest cosmic structures. As research continues, scientists hope to unlock the secrets of dark matter, shedding light on one of the most profound mysteries of the cosmos. Evidence for dark matter comes from various astronomical observations and phenomena. One of the earliest indications was the rotation curves of galaxies. In spiral galaxies, stars at the outer edges rotate faster than can be explained by the visible matter alone. This discrepancy suggests the presence of an unseen mass, providing additional gravitational pull. Gravitational lensing offers another strong piece of evidence. Light from distant objects is bent by massive galaxy clusters, indicating more mass than is visible. The cosmic microwave background, or CMB, also supports the existence of dark matter. The patterns in the CMB reveal the influence of dark matter on the early universe's structure. Galaxy cluster observations, such as those involving the Bullet cluster, show dark matter's gravitational effects. In collisions between galaxy clusters, dark matter separates from visible matter, revealing its presence. Studies of large-scale structures in the universe show a web-like pattern of galaxies and clusters. Dark matter forms the backbone of this cosmic web, shaping the distribution of visible matter. X-ray observations of galaxy clusters provide additional evidence. The hot gas in clusters emits X-rays, and its distribution suggests the presence of dark matter holding the cluster together. The movement of galaxies within clusters also points to dark matter. Galaxies move faster than expected based on visible mass, indicating additional unseen mass. Dark matter's influence extends to the growth of cosmic structures. Without dark matter, the universe's large-scale structures would not have formed as we observe them today. The study of galaxy formation and evolution further supports dark matter. Simulations show that dark matter is essential for creating the galaxies and clusters we see. Gravitational waves offer indirect evidence as well. The distribution and behavior of matter during events like black hole mergers can be influenced by dark matter. Microlensing events, where dark objects pass in front of stars, can also hint at dark matter. These events cause temporary brightness changes, suggesting the presence of compact dark matter objects. Experimental searches for dark matter particles, such as those conducted deep underground, seek to detect interactions with ordinary matter. While direct detection remains elusive, these experiments provide constraints on dark matter properties. Cosmological models incorporating dark matter align closely with observations. The lambda cold. Dark matter model, for example, accurately describes the universe's evolution. The combined evidence from various fields makes a compelling case for dark matter. Its gravitational effects on visible matter, light, and cosmic structures are undeniable. As research continues, scientists aim to uncover the exact nature of this mysterious substance. Understanding dark energy is one of the most significant challenges in cosmology. It is the mysterious force driving the accelerated expansion of the universe. Dark energy makes up about 70% of the universe's total energy density. Its exact nature is still unknown, but its effects are observed through its influence on cosmic expansion. The discovery of dark energy came from observing distant type Ia supernovae. These supernovae appear dimmer than expected, indicating that the universe's expansion rate is increasing. Dark energy is often associated with the cosmological constant, a term introduced by Einstein in his equations of general relativity. The cosmological constant represents a constant energy density filling space uniformly. However, the cosmological constant is just one possible explanation. Some theories propose that dark energy is dynamic, changing over time, and is described by fields such as quintessence. Observations of the cosmic microwave background provide insights into dark energy. The CMB data shows the impact of dark energy on the universe's geometry and expansion history. Large-scale galaxy surveys help map the distribution of dark energy. These surveys measure the distances and redshifts of galaxies to understand how dark energy influences their distribution. Gravitational lensing studies also contribute to our understanding. Dark energy affects the way light from distant galaxies is bent by massive objects, offering clues about its properties. Baryon acoustic oscillations, which are regular patterns in the distribution of galaxies, serve as a standard ruler for measuring cosmic distances. These measurements help determine the expansion rate and the influence of dark energy. One of the biggest questions is whether dark energy is constant or varying over time. Understanding this could reveal whether the universe will continue to expand indefinitely or change its behavior in the future. Advanced telescopes and space missions, such as the Euclid satellite and the James Webb Space Telescope, aim to study dark energy in more detail. These instruments will provide more precise data on its effects. Dark energy's influence extends to the fate of the universe. It affects how galaxies form and evolve, and it will determine the ultimate destiny of the cosmos. Theoretical physicists are exploring various models to explain dark energy. These include modifications to general relativity and new particle physics theories. Understanding dark energy could lead to new insights into fundamental physics. It challenges our current understanding of gravity, space, and time. As research progresses, scientists hope to unlock the secrets of dark energy. This knowledge will transform our understanding of the universe's past, present, and future. The quest to understand dark energy continues to drive advancements in cosmology. It remains one of the most intriguing and important areas of scientific inquiry. Dark energy plays a crucial role in the cosmic expansion of the universe. It counteracts the gravitational pull of matter, causing the expansion rate to accelerate. Before dark energy became dominant, the universe's expansion was slowing down due to gravity. This deceleration was influenced by the density of matter and radiation. As the universe expanded and matter became more diluted, dark energy's influence grew stronger. Around 5 billion years ago, it started to dominate, leading to accelerated expansion. This accelerated expansion means that galaxies are moving away from each other at increasing speeds. The farther away a galaxy is, the faster it recedes, influenced by the expanding space between them. The effect of dark energy is observed in the redshift of distant galaxies. Higher redshifts indicate that galaxies are moving away more rapidly, consistent with an accelerating universe. Dark energy affects the large-scale structure of the universe. It influences how galaxies cluster and form, altering the growth of cosmic structures over time. It also impacts the geometry of the universe. Observations of the cosmic microwave background show a flat geometry, which is consistent with a universe dominated by dark energy. The accelerated expansion driven by dark energy has implications for the fate of the universe. If it continues to dominate, the universe will keep expanding indefinitely. This leads to scenarios like the Big Freeze, where galaxies drift apart, star formation ceases, and the universe cools and darkens over time. Alternatively, in the Big Rip scenario, dark energy could eventually tear apart galaxies, stars, and even atoms. Dark energy also challenges our understanding of fundamental physics. It raises questions about the nature of vacuum energy and the cosmological constant problem. To study dark energy's role, scientists used large-scale surveys and advanced telescopes. These tools measured the distribution of galaxies and the effects of dark energy on their movement. Gravitational lensing studies provide additional insights. By examining how light is bent by massive objects, researchers can infer the influence of dark energy on cosmic structures. Theoretical models of dark energy explore various possibilities, from a constant cosmological constant to dynamic fields like quintessence. These models aim to explain its properties and effects on the universe. Understanding dark energy's role in cosmic expansion is crucial for a comprehensive picture of the universe. It connects the smallest scales of particle physics with the largest scales of cosmology. As research continues, the goal is to uncover the true nature of dark energy. This will enhance our understanding of the universe's past, present, and future, offering profound insights into the workings of the cosmos. The discovery of dark energy has had a significant impact on the Big Bang theory. It has added a new dimension to our understanding of the universe's expansion. Originally, the Big Bang theory described a universe that expanded from a hot, dense state and gradually slowed down due to gravity. The presence of dark energy changed this view. Dark energy explains why the expansion of the universe is accelerating rather than slowing down. This acceleration was unexpected and has led to revisions in the Big Bang model. The introduction of dark energy has required adjustments in cosmological equations. These adjustments account for the accelerating expansion observed in distant galaxies. Dark energy also affects our understanding of the universe's age. By influencing the expansion rate, it helps refine estimates of how long the universe has been expanding since the Big Bang. The role of dark energy in the early universe is still a subject of research. Understanding its properties could provide insights into the conditions of the universe shortly after the Big Bang. The cosmic microwave background data supports the existence of dark energy. It shows patterns that are consistent with an accelerating universe, influenced by dark energy. Dark energy's impact extends to the formation of large-scale structures. It affects how galaxies and clusters form and evolve over billions of years. The concept of a cosmological constant, revived by the discovery of dark energy, was initially introduced by Einstein. This constant is now a central part of the Big Bang theory. The inclusion of dark energy has also led to the development of new models. These models explore various scenarios for the universe's future, including continued expansion and eventual decay. Dark energy challenges some aspects of classical cosmology. It raises questions about the nature of space, time, and the fundamental forces that govern the universe. Research into dark energy is ongoing, with many experiments designed to understand its properties. These include space-based observatories and ground-based telescopes. The study of dark energy has led to collaborations between different fields of science. Physicists, astronomers, and cosmologists work together to uncover its mysteries. Understanding dark energy is crucial for a complete picture of the universe. It connects the initial conditions of the Big Bang with the current and future state of the cosmos. As our knowledge of dark energy grows, it continues to shape and refine the Big Bang theory. This ongoing research promises to reveal more about the fundamental nature of the universe and its origins. Telescopic observations have been crucial in advancing our understanding of the universe. They provide detailed images and data on distant galaxies, stars, and cosmic phenomena. The Hubble Space Telescope has been a key instrument in these observations. It has captured stunning images of deep space, revealing the structure and composition of galaxies. Observations from Hubble have confirmed the accelerating expansion of the universe. By studying distant supernovae, it provided critical evidence for the existence of dark energy. Ground-based telescopes also play a significant role. Large observatories, like the Keck Observatory in Hawaii, offer high-resolution images and spectroscopic data. These telescopes have mapped the distribution of galaxies, helping to understand the large-scale structure of the universe. They provide insights into how galaxies cluster and evolve. Radio telescopes, such as the Very Large Array, observe radio waves from space. They detect signals from distant galaxies and cosmic phenomena, contributing to our understanding of the universe's evolution. Infrared telescopes, like the Spitzer Space Telescope, observe heat emitted by celestial objects. They reveal information about star formation and the composition of galaxies. X-ray telescopes, such as the Chandra X-ray Observatory, detect high-energy radiation. They study phenomena like black holes and supernova remnants, providing insights into the extreme conditions of the universe. The James Webb Space Telescope, set to launch soon, will offer even more advanced capabilities. It will observe in the infrared spectrum, allowing it to see further into the past and study the formation of the first galaxies. Telescopic observations also help identify exoplanets. Instruments like the Kepler Space Telescope have discovered thousands of planets orbiting other stars, expanding our understanding of planetary systems. These observations contribute to the study of cosmic microwave background radiation. Telescopes like the Planck satellite provide detailed maps of this radiation, offering clues about the early universe. Telescopes also observe gravitational lensing. This phenomenon, where light is bent by massive objects, helps map dark matter and study the distribution of mass in the universe. Optical telescopes, both on the ground and in space, capture visible light from celestial objects. They provide detailed images and spectra, revealing the composition and motion of stars and galaxies. Future telescopes, like the Extremely Large Telescope, promise to revolutionize our understanding further. They will offer unprecedented resolution and sensitivity, probing deeper into the cosmos. Telescopic observations are essential for testing and refining cosmological models. They connect theoretical predictions with real data, enhancing our understanding of the universe's structure and evolution. Cosmic microwave background studies are crucial for understanding the early universe. The CMB is the afterglow of the Big Bang, providing a snapshot of the universe 380,000 years after its birth. Satellites like COBE, WMAP, and Planck have been instrumental in studying the CMB. These missions have mapped the tiny temperature fluctuations across the sky. COBE was the first to detect these fluctuations, confirming the CMB's blackbody spectrum. This discovery provided strong evidence for the Big Bang theory. WMAP improved upon COBE's measurements, offering higher resolution data. It revealed detailed patterns of the CMB, helping to refine our understanding of the universe's age and composition. Planck has provided the most precise measurements to date. Its data has allowed scientists to create the most detailed map of the CMB, showing minute variations in temperature. These temperature fluctuations are essential for understanding the formation of large-scale structures. They represent the seeds of galaxies and clusters, showing how matter was distributed in the early universe. The CMB also offers insights into the universe's curvature. Observations indicate that the universe is flat, consistent with the predictions of the inflationary model. Studying the polarization of the CMB provides additional information. Polarization patterns help scientists understand the physics of the early universe and the influence of gravitational waves. The CMB's data helps determine key cosmological parameters. This includes the Hubble constant, the density of dark matter and dark energy, and the overall geometry of the universe. Anomalies in the CMB, such as the cold spot, challenge current models. These features are areas of intense study, offering potential clues about new physics or cosmic events. The CMB also helps test theories of cosmic inflation. By studying the detailed patterns of the CMB, scientists can learn about the rapid expansion that occurred fractions of a second after the Big Bang. Cosmic microwave background studies continue to evolve with new technology. Future missions aim to provide even higher resolution data and more precise measurements. These studies connect observations of the early universe with its current state. They bridge the gap between the initial conditions of the Big Bang and the formation of galaxies and other structures. Understanding the CMB is crucial for a complete picture of cosmology. It provides a wealth of information about the universe's origins, composition, and evolution. As research continues, the cosmic microwave background remains a cornerstone of observational cosmology. It offers a unique window into the universe's earliest moments and the fundamental processes that shaped it. Redshift surveys are essential tools for mapping the universe. They measure the redshift of galaxies to determine their distance and velocity. These surveys provide a three-dimensional map of the universe. By mapping the positions of galaxies, they reveal the large-scale structure of the cosmos. The Sloan Digital Sky Survey is one of the most significant redshift surveys. It has mapped over 1 million galaxies, providing detailed information about their distribution. Redshift surveys help us understand how galaxies cluster. These clusters are influenced by the distribution of dark matter and the overall structure of the universe. The data from Redshift surveys supports the theory of an expanding universe. By measuring how galaxies move away from us, they provide evidence for the Hubble law. These surveys also help in studying dark energy. By analyzing the large-scale structure of the universe, scientists can infer the effects of dark energy on cosmic expansion. Redshift surveys reveal the cosmic web, a vast network of galaxies and dark matter. This web-like structure shows how matter is distributed on the largest scales. The Baryon Oscillation Spectroscopic Survey, or BOSS, is another important Redshift survey. It studies the distribution of galaxies to understand the effects of dark energy. Redshift data helps in understanding the growth of cosmic structures. By observing how galaxy clusters form and evolve, scientists gain insights into the history of the universe. These surveys also contribute to the study of galaxy evolution. By mapping galaxies at different distances, they provide a timeline of how galaxies have changed over billions of years. Redshift surveys can detect rare and unusual objects. They help identify distant quasars, massive galaxy clusters, and other significant structures. The data from these surveys is used to test cosmological models. By comparing observations with theoretical predictions, scientists can refine their understanding of the universe. Future Redshift surveys aim to map even larger volumes of the universe. Projects like the Dark Energy Spectroscopic Instrument, or DESI, will provide unprecedented detail. Redshift surveys are crucial for understanding the overall dynamics of the cosmos. They connect the motions of galaxies with the expansion and structure of the universe. These surveys continue to enhance our understanding of the universe. They provide vital data that helps unravel the mysteries of cosmic evolution and the nature of dark energy and dark matter. Gravitational lensing is a phenomenon where light from distant objects is bent by the gravity of massive objects. This effect was predicted by Einstein's theory of general relativity. There are two main types of gravitational lensing: strong and weak lensing. Strong lensing creates multiple images, arcs, or even rings of the background object, while weak lensing subtly distorts the shapes of background galaxies. Strong gravitational lensing can produce striking visual effects. For example, it can create Einstein rings, where the background object forms a complete ring around the lensing mass. Weak gravitational lensing requires statistical analysis to detect. By measuring the slight distortions in the shapes of many galaxies, scientists can map the distribution of dark matter. Gravitational lensing is a powerful tool for studying dark matter. Since dark matter does not emit light, lensing provides one of the few ways to directly observe its distribution. Lensing also allows astronomers to study distant galaxies that would otherwise be too faint to see. The magnification effect of lensing makes these distant objects appear brighter and larger. By analyzing lensing effects, scientists can measure the mass of galaxy clusters. This helps in understanding the total mass, including both visible and dark matter, in these clusters. Gravitational lensing has been used to discover exoplanets. Microlensing events, where a star's gravity temporarily magnifies a background star, can reveal planets orbiting the lensing star. Lensing effects also provide insights into the expansion rate of the universe. By studying how the light from distant objects is bent, scientists can infer the Hubble constant. Gravitational lensing helps test general relativity on cosmic scales. The way light bends around massive objects can confirm or challenge predictions of Einstein's theory. The study of lensing is crucial for understanding the large-scale structure of the universe. It reveals how matter is distributed and how it evolves over time. Advanced telescopes and surveys continue to enhance our understanding of lensing. Instruments like the Hubble Space Telescope have provided detailed images of lensing events. Future missions, such as the Euclid satellite, aim to map weak lensing over large areas of the sky. This will provide detailed data on the distribution of dark matter and the effects of dark energy. Gravitational lensing connects observations of distant galaxies with fundamental physics. It provides a unique window into the nature of gravity, dark matter, and the overall structure of the universe. The study of lensing continues to reveal new insights about the cosmos. It remains one of the most exciting and informative tools in modern astronomy. Particle physics experiments are crucial for understanding the fundamental particles and forces that govern the universe. These experiments are often conducted using particle accelerators. The Large Hadron Collider, or LHC, at CERN, is the world's largest and most powerful particle accelerator. It smashes protons together at high speeds to study the resulting particles. One of the major discoveries at the LHC was the Higgs boson in 2012. The Higgs boson is a fundamental particle that gives other particles their mass. Experiments at the LHC explore conditions similar to those just after the Big Bang. By recreating these conditions, scientists can study the early universe's fundamental properties. Particle accelerators also investigate dark matter. While dark matter has not yet been directly detected, experiments aim to produce dark matter particles and observe their interactions. Neutrino experiments are another important area of particle physics. Neutrinos are incredibly light and weakly interacting particles, making them difficult to detect. Experiments like those at the IceCube Neutrino Observatory detect neutrinos by observing their interactions in large volumes of ice. These studies help understand neutrino properties and their role in the universe. Proton decay experiments aim to test grand unified theories that predict protons can decay into lighter particles. Detecting proton decay would provide insights into the fundamental forces of nature. Particle physics experiments also study the behavior of quarks and gluons. These particles make up protons and neutrons and are held together by the strong nuclear force. The study of antimatter is another key focus. By comparing matter and antimatter, experiments test fundamental symmetries in physics and help explain the matter-antimatter asymmetry in the universe. High-energy particle collisions produce exotic particles, allowing scientists to explore theories beyond the standard model. These experiments probe the existence of supersymmetry, extra dimensions, and other advanced concepts. Precision measurements of particle properties, such as their masses and lifetimes, provide crucial data for testing theoretical models. These measurements refine our understanding of fundamental physics. Particle physics experiments are often international collaborations. Facilities like CERN involve scientists from around the world, working together to uncover the universe's deepest secrets. Advancements in detector technology continue to improve the sensitivity and precision of particle physics experiments. This progress opens new avenues for discovery and enhances our understanding of the cosmos. Understanding the fundamental particles and forces is essential for a complete picture of the universe. Particle physics experiments connect the smallest scales of nature with the largest structures in the cosmos. The steady-state theory was an alternative to the Big Bang theory, proposed in the mid-20th century. It suggested that the universe has no beginning or end, and has always existed in a constant state. This theory posited that new matter is continuously created as the universe expands. This creation of matter would keep the density of the universe constant over time. The steady-state theory was proposed by Fred Hoyle, Thomas Gold, and Hermann Bondi. They argued that this model avoided the need for a beginning, which they saw as a problematic concept. In this theory, galaxies move apart, but new galaxies form from the newly created matter. This process would keep the universe looking roughly the same at all times. One of the key motivations for the steady-state theory was the philosophical preference for an eternal, unchanging universe. It avoided the implications of a finite beginning, which some scientists found troubling. The discovery of the cosmic microwave background radiation in 1965 provided strong evidence against the steady-state theory. The CMB is a remnant of the Big Bang, indicating a hot, dense origin for the universe. Observations of distant galaxies also contradicted the steady-state theory. These galaxies appear younger and different from nearby galaxies, suggesting an evolving universe. The abundance of light elements, such as helium and deuterium, is consistent with predictions from the Big Bang nucleosynthesis. The steady-state theory could not account for these observations. The steady-state theory also struggled to explain the observed large-scale structure of the universe. The distribution of galaxies and galaxy clusters fits better with a model of cosmic evolution from the Big Bang. Despite these challenges, the steady-state theory contributed to the development of cosmology. It prompted debates and further research that advanced our understanding of the universe. Fred Hoyle, a key proponent of the steady-state theory, made significant contributions to astrophysics. including the understanding of stellar nucleosynthesis. His work helped explain how elements are formed in stars. The steady-state theory also led to the exploration of other alternative models. These models aim to address some of the philosophical and scientific questions raised by the concept of a finite beginning. While the Big Bang theory is now the dominant model, the steady-state theory played a role in shaping modern cosmological thought. It highlighted the importance of observational evidence in testing and refining theories. The decline of the steady-state theory demonstrates the scientific process. Theories must be tested against observations, and those that do not fit the data are modified or replaced. Understanding the history of the steady-state theory provides context for the development of modern cosmology. It shows how scientific ideas evolve and how evidence drives our understanding of the universe. The Epyrotic model is an alternative to the Big Bang theory. It proposes that the universe was formed from the collision of two three-dimensional worlds, or branes, in a higher dimensional space. This model suggests that these branes collided, creating the hot, dense state we associate with the Big Bang. Instead of a singularity, the universe's origin involves a cyclical process. The term Epyrotic comes from a Greek word meaning conflagration, or out of fire, reflecting the fiery collision that births the universe. This idea contrasts with the Big Bang's concept of a singular beginning. In the Epyrotic model, the universe undergoes periods of expansion and contraction. These cycles can repeat indefinitely, avoiding the concept of a single creation event. This model aims to address some of the issues with the Big Bang theory, such as the horizon and flatness problems. The collision of branes can naturally lead to the uniformity and flatness observed in the universe. One of the key features of the Epyrotic model is that it does not require cosmic inflation. Instead, the conditions before and during the brane collision set the stage for the universe's expansion. The model was developed by physicists, including Paul Steinhardt and Neil Turok. It builds on concepts from string theory and higher dimensional physics. The Epyrotic model also provides a different perspective on dark energy. It suggests that dark energy could be related to the dynamics of branes in higher dimensional space. Observational tests for the Epyrotic model involve studying the cosmic microwave background. The model predicts specific patterns in the CMB that differ from those predicted by inflationary models. Despite its intriguing aspects, the Epyrotic model faces challenges. It must explain the detailed properties of the CMB and the large-scale structure of the universe as accurately as the Big Bang theory. The model also requires complex mathematics and advanced concepts from string theory. This complexity makes it difficult to test and verify through observations. While not as widely accepted as the Big Bang theory, the Epyrotic model has spurred further research into alternative cosmologies. It encourages scientists to explore new ideas and address unresolved questions. The cyclical nature of the Epyrotic model has philosophical appeal. It suggests an eternal universe with no beginning or end, constantly renewing itself through brane collisions. As research progresses, scientists continue to refine the Epyrotic model. They aim to develop predictions that can be tested with current and future observations. Understanding alternative models like the Epyrotic model is essential for a complete picture of cosmology. It highlights the diversity of ideas in the quest to understand the universe's origins and evolution. The multiverse theory suggests that our universe is just one of many universes that exist. These parallel universes collectively form what is known as the multiverse. There are several different versions of the multiverse theory. Some propose that each universe has different physical laws and constants, while others suggest that they are all variations of our own universe. One version of the multiverse arises from the concept of eternal inflation. This idea extends the inflationary model of the universe, suggesting that inflation never stops and constantly creates new, separate universes. Another version comes from string theory. In this context, different universes are formed in different regions of a vast higher dimensional space. Quantum mechanics also offers a basis for the multiverse theory. The many worlds interpretation suggests that every quantum event spawns new universes for each possible outcome. The multiverse theory addresses some fundamental questions in cosmology. It provides possible explanations for the fine-tuning of physical constants in our universe. If there are many universes with different properties, It's not surprising that at least one, like ours, has the conditions suitable for life. This concept is known as the anthropic principle. Observational evidence for the multiverse is challenging to obtain. Since these other universes are separate from our own, direct observation is currently impossible. However, indirect evidence might come from cosmic anomalies. Some theories suggest that interactions between universes could leave detectable imprints on the cosmic microwave background. The concept of the multiverse also has implications for understanding the nature of reality. It challenges the notion of a single, unique universe and suggests a broader, more complex structure. Critics of the multiverse theory argue that it is untestable and therefore not scientific. They suggest that without observational evidence, the theory remains speculative. Proponents argue that the theory offers a natural extension of current cosmological models. It encourages exploration of new ideas and possibilities in understanding the universe. The multiverse theory has found interest beyond physics, influencing philosophy and science fiction. It raises questions about the nature of existence and the limits of human knowledge. Research into the multiverse continues to evolve. Scientists are developing new theoretical models and seeking potential ways to test these ideas. Understanding the multiverse theory provides insight into the diverse range of ideas in modern cosmology. It highlights the ongoing quest to explain the origins and nature of the universe. Quantum gravity models aim to unify quantum mechanics and general relativity. These models seek to describe gravity according to the principles of quantum mechanics. One of the leading approaches is string theory. It proposes that fundamental particles are not point-like but rather tiny, vibrating strings. String theory suggests that different vibrational modes of these strings correspond to different particles. It also introduces additional dimensions beyond the familiar three spatial dimensions and one time dimension. Another approach is loop quantum gravity. This theory posits that space-time itself has a discrete structure, composed of tiny loops. Loop quantum gravity attempts to quantize space-time without requiring extra dimensions. It focuses on the geometry of space-time at the smallest scales. Both string theory and loop quantum gravity aim to resolve the singularities predicted by general relativity, such as those found in black holes and the Big Bang. These singularities indicate points where the laws of physics break down. Quantum gravity models also strive to explain how gravity works at the Planck scale. This is the scale at which quantum effects become significant for gravity. String theory includes the concept of supersymmetry, where each particle has a superpartner with different spin properties. Supersymmetry could help resolve some of the inconsistencies between quantum mechanics and general relativity. Loop quantum gravity predicts that space-time is quantized, meaning it has a smallest possible unit. This quantization could prevent the infinite densities associated with singularities. Experimental evidence for quantum gravity models is currently lacking. Testing these theories is challenging because the effects of quantum gravity are expected to be observable only at extremely high energies or tiny scales. Researchers hope to find indirect evidence through phenomena such as black hole thermodynamics, cosmic microwave background anomalies, or gravitational wave observations. Quantum gravity models also explore the possibility of a quantum theory of space-time. This theory would describe how space and time themselves emerge from more fundamental quantum processes. Advances in technology and experimental techniques may eventually provide the means to test these models. High-energy particle colliders and advanced telescopes could offer new insights. Understanding quantum gravity is crucial for a complete theory of everything. It would unify the fundamental forces of nature and provide a deeper understanding of the universe's fundamental structure. Research in this field is ongoing, with scientists exploring various theoretical frameworks. The pursuit of a successful quantum gravity model remains one of the most profound challenges in modern physics. Comparing quantum gravity models with the Big Bang theory highlights their different approaches to understanding the universe. The Big Bang theory explains the universe's expansion from a hot, dense state, while quantum gravity models seek to describe the nature of space-time itself. The Big Bang theory is well supported by observational evidence, such as the cosmic microwave background radiation and the distribution of galaxies. These observations confirm that the universe has been expanding for about 13.8 billion years. Quantum gravity models, on the other hand, are more theoretical. They aim to reconcile general relativity, which describes gravity, with quantum mechanics, which describes the other fundamental forces. String theory, a prominent quantum gravity model, introduces the concept of extra dimensions. These dimensions are compactified and not directly observable, adding complexity to the model. Loop quantum gravity, another approach, avoids extra dimensions and instead focuses on the discrete nature of space-time. It proposes that space-time is composed of tiny loops, offering a different perspective from string theory. The Big Bang theory does not address what happened before the initial expansion. Quantum gravity models attempt to explore this by providing a framework that could describe the conditions preceding the Big Bang. Both theories aim to resolve the singularity problem associated with the Big Bang. Quantum gravity models suggest that singularities may not exist when space-time is quantized. The Big Bang theory has made specific, testable predictions, many of which have been confirmed. Quantum gravity models are more difficult to test directly as they require extremely high energies or very small scales. In terms of unification, the Big Bang theory does not integrate all fundamental forces, whereas quantum gravity models seek a unified description of all forces, including gravity. Quantum gravity models could potentially provide insights into dark matter and dark energy, components of the universe that the Big Bang theory does not fully explain. These models offer new possibilities for understanding the universe's composition. While the Big Bang theory describes the universe's evolution from a hot, dense state, quantum gravity models explore the fundamental nature of spacetime, potentially offering a more comprehensive picture of the cosmos. The development of quantum gravity models is driven by theoretical advances rather than observational data. This contrasts with the Big Bang theory, which has been shaped by extensive astronomical observations. And both approaches are essential for advancing our understanding of the universe. The Big Bang theory provides a successful framework for describing cosmic history, while quantum gravity models push the boundaries of fundamental physics. Future discoveries and technological advancements may bridge the gap between these theories. New observations and experiments could provide the evidence needed to support or refine quantum gravity models. Ultimately, the comparison between the Big Bang theory and quantum gravity models highlights the ongoing quest to understand the universe's origins and fundamental nature. Both perspectives contribute to a deeper and more complete picture of the cosmos. Advancements in telescope technology have revolutionized our understanding of the universe. Modern telescopes can observe celestial objects in various wavelengths, providing a comprehensive view of the cosmos. The Hubble Space Telescope has been a game-changer. Since its launch in 1990, it has captured detailed images of distant galaxies, nebulae, and other astronomical phenomena. Hubble's observations have confirmed the accelerated expansion of the universe. By studying distant supernovae, it provided crucial evidence for the existence of dark energy. Ground-based telescopes have also seen significant improvements. Adaptive optics technology allows them to correct for atmospheric distortions, resulting in clearer and sharper images. The Very Large Telescope in Chile uses adaptive optics to observe stars and planets with unprecedented clarity. This technology enables astronomers to study objects in great detail from the Earth's surface. Radio telescopes have expanded our ability to detect radio waves from space. The Atacama Large Millimeter Array, or ALMA, provides high-resolution images of the cold universe, revealing the birthplaces of stars and planets. Infrared telescopes like the Spitzer Space Telescope observe heat emitted by celestial objects. They penetrate dust clouds to reveal hidden regions of star formation. X-ray telescopes, such as the Chandra X-ray Observatory, detect high-energy radiation. They study the violent processes around black holes, neutron stars, and supernova remnants. The upcoming James Webb Space Telescope promises to further advance our knowledge. It will observe in the infrared spectrum, allowing it to look back to the earliest galaxies formed after the Big Bang. Space-based telescopes avoid atmospheric interference, offering clearer views of the universe. They complement ground-based observatories by providing data that is not possible to obtain from Earth. Advancements in telescope technology also include improvements in data processing and analysis. High-performance computers and algorithms allow scientists to handle and interpret vast amounts of observational data. Multi-wavelength observations provide a more complete picture of astronomical objects, By combining data from different types of telescopes, astronomers can study the same object in multiple ways. Telescope arrays, like the Square Kilometre Array, are set to revolutionize radio astronomy. This project will be the largest radio telescope ever built, capable of surveying the sky with unmatched sensitivity. These technological advancements are driving discoveries across all areas of astronomy. From exoplanets to dark matter, they continue to expand our understanding of the universe. As telescope technology continues to improve, future discoveries will likely reshape our knowledge of the cosmos. These advancements ensure that astronomy remains a dynamic and rapidly evolving field of science. Space missions have played a crucial role in advancing our understanding of the universe. The Hubble Space Telescope, launched in 1990, has provided stunning images and invaluable data on distant galaxies and cosmic phenomena. Hubble's observations have helped determine the rate of expansion of the universe. It has also provided evidence for the existence of dark energy, contributing significantly to cosmology. The Planck satellite, launched by the European Space Agency, mapped the cosmic microwave background with high precision. Its data has refined our understanding of the universe's age, composition, and initial conditions. Planck's observations have confirmed the standard model of cosmology. They have provided insights into the early universe, supporting the theory of inflation. The James Webb Space Telescope, set to launch soon, will observe the universe in infrared. This will allow it to peer through dust clouds and study the formation of stars and galaxies in greater detail. The Chandra X-ray Observatory, launched in 1999, has revolutionized our understanding of high-energy processes in the universe. It observes X-rays from black holes, supernovae, and hot gas in galaxy clusters. The Spitzer Space Telescope has observed the universe in infrared light. It has revealed hidden regions of star formation and discovered new exoplanets. The Kepler Space Telescope focused on finding exoplanets. It identified thousands of potential planets orbiting other stars, greatly expanding our knowledge of planetary systems. The Gaia mission, launched by the European Space Agency, is mapping the positions and motions of over 1 billion stars. This data helps us understand the structure and evolution of our galaxy. The Hubble Deep Field images provided a glimpse into the early universe. By observing a small patch of sky for an extended period, Hubble revealed thousands of distant galaxies. The Cosmic Background Explorer, or COBE, was an earlier mission that measured the cosmic microwave background. Its data confirmed the Big Bang theory and earned its team a Nobel Prize. The Wilkinson Microwave Anisotropy Probe, or WMAP, mapped temperature fluctuations in the cosmic microwave background. This mission provided detailed information about the universe's age, composition, and development. The Fermi Gamma Ray Space Telescope observes the most energetic phenomena in the universe. It has provided insights into gamma-ray bursts, black holes, and active galactic nuclei. Future missions like the Nancy Grace Roman Space Telescope aim to study dark energy and exoplanets. These missions will continue to push the boundaries of our understanding. And space missions have transformed our view of the universe. They provide critical data that complements ground-based observations, helping to answer fundamental questions about the cosmos. Particle accelerators play a crucial role in understanding the fundamental particles and forces of the universe. They accelerate particles to high speeds and collide them, allowing scientists to study the resulting interactions. The Large Hadron Collider, or LHC, at CERN, is the most powerful particle accelerator in the world. It has made significant discoveries, including the Higgs boson, which confirms the mechanism that gives particles their mass. Particle accelerators recreate conditions similar to those just after the Big Bang. By studying these high-energy collisions, researchers gain insights into the fundamental forces and particles that shaped the early universe. Accelerators help test predictions of the standard model of particle physics. They allow scientists to observe rare particles and interactions that are not seen in nature under normal conditions. These experiments explore the properties of quarks, gluons, and other subatomic particles. Understanding these particles helps explain the structure of protons, neutrons, and the nuclei of atoms. Particle accelerators are also used to search for new particles beyond the standard model. This includes hypothetical particles like those predicted by supersymmetry and other advanced theories. High-energy collisions at the LHC have provided evidence for the existence of quark-gluon plasma. This state of matter existed just microseconds after the Big Bang and helped scientists understand the early universe. Accelerators contribute to the study of antimatter. By producing and observing antimatter particles, researchers explore the matter-antimatter asymmetry in the universe. The precise measurements obtained from particle accelerators refine our understanding of fundamental constants. This includes the masses and lifetimes of particles, which are crucial for testing theoretical models. Neutrino experiments at accelerators provide insights into the properties of these elusive particles. Neutrinos interact very weakly with matter, making them challenging to study but essential for understanding the universe. Accelerators also investigate the strong nuclear force, which binds quarks together in protons and neutrons. These studies are essential for understanding the stability and interactions of atomic nuclei. Experiments with particle accelerators have practical applications as well. They contribute to the development of medical technologies, such as cancer treatment through proton therapy. The data from accelerators help address questions about dark matter. While dark matter particles have not been detected directly, accelerator experiments provide constraints on their properties. Particle accelerators involve international collaborations. Facilities like CERN bring together scientists from around the world to conduct cutting-edge research. The advancements in particle accelerator technology continue to push the boundaries of physics. Future accelerators promise to explore even higher energies and uncover new phenomena, further enhancing our understanding of the universe. Supercomputing plays a vital role in modern cosmology. These powerful computers handle the vast amounts of data generated by telescopes and particle accelerators. Simulations of the universe's evolution require immense computational power. Supercomputers model the formation of galaxies, stars, and large-scale structures over billions of years. These simulations help scientists understand complex processes that cannot be directly observed. They provide insights into the behavior of dark matter, dark energy, and the fundamental forces of nature. Supercomputers also analyze data from cosmic microwave background observations. They process the detailed measurements needed to map temperature fluctuations and polarization patterns. The simulations explore different cosmological models. By comparing the results with observational data, scientists can test theories and refine our understanding of the universe's history. These models require solving complex equations that describe gravity, fluid dynamics, and thermodynamics. Supercomputers handle these calculations efficiently, enabling more accurate simulations. One of the most significant projects is the Millennium Simulation. It tracks the evolution of millions of galaxies and dark matter particles, providing a detailed view of the universe's large-scale structure. Supercomputers also assist in the search for dark matter and dark energy. They simulate potential interactions and behaviors, helping to design experiments and interpret results. Advanced algorithms run on supercomputers to detect patterns in large datasets. This includes identifying gravitational lensing effects, galaxy clusters, and other cosmic phenomena. These computations help refine measurements of the Hubble constant. By simulating the expansion of the universe, supercomputers contribute to resolving the discrepancies in its value. The processing power of supercomputers accelerates the analysis of data from surveys like the Sloan Digital Sky Survey. They enable rapid processing of images and spectra from millions of galaxies. Supercomputers are crucial for predicting the outcomes of particle collisions in accelerators. They simulate high-energy physics experiments, guiding the search for new particles and interactions. The development of new computational techniques continues to enhance the capabilities of supercomputers. Machine learning and artificial intelligence are increasingly used to analyze and interpret cosmological data. These advancements drive discoveries across all areas of astronomy and physics. Supercomputers provide the tools needed to tackle the most profound questions about the universe. As technology progresses, supercomputers will become even more powerful. They will enable more detailed and extensive simulations, further advancing our understanding of the cosmos. Future technological prospects in cosmology are incredibly promising. Advances in telescope technology will provide even deeper views of the universe, allowing us to observe the earliest galaxies and stars. The James Webb Space Telescope, set to launch soon, will revolutionize our understanding of the cosmos. Its infrared capabilities will enable it to peer through dust clouds and study the formation of stars and planetary systems. New ground-based telescopes like the extremely large telescope in Chile will offer unprecedented resolution and sensitivity. These instruments will help us explore exoplanets and the conditions for life beyond Earth. Advancements in radio astronomy will come from projects like the Square Kilometre Array. This massive array will be the world's largest radio telescope, providing detailed maps of the universe's structure. Next-generation X-ray observatories will explore high-energy phenomena. They will study black holes, neutron stars, and the dynamics of galaxy clusters with greater precision. The development of space-based gravitational wave detectors, such as the Laser Interferometer Space Antenna, will open a new window into the universe. These detectors will observe gravitational waves from massive cosmic events. In particle physics, future accelerators will probe even higher energies. Projects like the proposed Future Circular Collider aim to explore conditions closer to the Big Bang, searching for new particles and forces. Supercomputing power will continue to grow, enabling more complex and detailed simulations. These simulations will help refine our understanding of cosmic evolution and the fundamental laws of physics. Artificial intelligence and machine learning will play an increasingly important role. These technologies will analyze vast amounts of data, identifying patterns and making new discoveries faster than ever before. Quantum computing holds the potential to revolutionize cosmology. It could solve complex problems that are currently intractable, providing new insights into the nature of the universe. Innovations in detector technology will improve the sensitivity of dark matter and dark energy experiments. These advancements will help us understand these mysterious components of the universe. Enhanced collaboration between international space agencies will drive progress. Joint missions and shared data will accelerate discoveries and expand our knowledge of the cosmos. New materials and manufacturing techniques will lead to lighter, more efficient spacecraft and instruments. This will make deep space exploration more feasible and cost-effective. The miniaturization of technology will enable the deployment of swarms of small, specialized satellites. These satellite constellations will provide comprehensive coverage and detailed observations of the universe. As we look to the future, the prospects for technological advancements in cosmology are boundless. These innovations will continue to push the frontiers of knowledge, uncovering the deepest secrets of the universe. The origins of space and time are fundamental questions in cosmology. Understanding how these dimensions came into existence is crucial for explaining the universe's beginnings. According to the Big Bang theory, space and time began 13.8 billion years ago. This theory posits that the universe expanded from an extremely hot and dense state. Before the Big Bang, the concepts of space and time as we understand them did not exist. The universe was in a singularity, a point where our current laws of physics break down. Cosmic inflation, a rapid expansion just after the Big Bang, shaped the structure of space-time. This inflationary period smoothed out the universe and set the stage for its subsequent expansion. Einstein's theory of general relativity describes how space and time are intertwined. In this framework, massive objects cause space-time to curve, which we perceive as gravity. Quantum mechanics, which governs the behavior of particles on the smallest scales, also plays a role in understanding the origins of space and time. However, reconciling it with general relativity remains a challenge. Theories of quantum gravity, like string theory and loop quantum gravity, attempt to unify these two frameworks. They suggest that space and time may be quantized at the smallest scales. String theory posits that the fundamental building blocks of the universe are tiny, vibrating strings. These strings could exist in multiple dimensions, beyond the familiar 3 dimensions of space and 1 of time. Loop quantum gravity proposes that space-time has a discrete structure, composed of tiny loops. This theory suggests that space and time are not continuous, but made up of finite pieces. The concept of a multiverse introduces the idea that our universe is just one of many. Each universe could have different properties, including different versions of space and time. The Epyrotic model offers an alternative to the Big Bang, proposing that our universe was formed from the collision of 2 higher-dimensional branes. This model provides a different perspective on the origins of space and time. Understanding the origins of space and time also involves studying the cosmic microwave background. This radiation provides a snapshot of the universe when it was just 380,000 years old, offering clues about its early conditions. Advances in technology, such as more powerful telescopes and particle accelerators, are essential for probing these questions. They help scientists test theories and gather data on the universe's earliest moments. The study of black holes and the information paradox also provides insights. These extreme environments push the boundaries of our understanding of space, time, and gravity. Exploring the origins of space and time is one of the most profound endeavors in science. It seeks to answer fundamental questions about the nature of reality and our place in the cosmos. The fate of the universe is a central question in cosmology. Understanding how the universe will end involves studying its current expansion and the forces at play. One possibility is the Big Freeze, where the universe continues to expand forever. In this scenario, galaxies move farther apart, and star formation slows down as available gas is used up. Eventually, existing stars will burn out, leaving behind white dwarfs, neutron stars, and black holes. Over time, these remnants will also fade, leading to a cold, dark universe. Another possibility is the Big Crunch. If the expansion of the universe slows and reverses, it could collapse back into a hot, dense state, potentially leading to a new Big Bang. The Big Rip is a more dramatic scenario. If dark energy's repulsive force increases over time, it could eventually tear apart galaxies, stars, and even atoms, ending the universe in a violent disintegration. The fate of the universe depends on the properties of dark energy. Observations suggest that dark energy makes up about 70% of the universe's total energy density and drives the current accelerated expansion. Determining the exact nature of dark energy is crucial for predicting the universe's future. Different models of dark energy lead to different outcomes for the universe's fate. The lambda cold dark matter model, or lambda CDM, is the standard cosmological model. It incorporates dark energy and dark matter, providing a framework for understanding the universe's expansion and evolution. Observations of the cosmic microwave background, galaxy clusters, and supernova help refine our understanding of dark energy and the universe's ultimate fate. These observations guide theoretical models and predictions. Gravitational wave astronomy could also provide insights into the fate of the universe. Studying the merger of massive objects might reveal more about the behavior of spacetime and dark energy. Understanding the universe's fate involves not only cosmology but also particle physics. The interactions and properties of fundamental particles play a role in the long-term evolution of the cosmos. Future space missions and advanced telescopes will continue to gather data. Projects like the James Webb Space Telescope and the Euclid satellite aim to improve our understanding of cosmic expansion and dark energy. The fate of the universe has profound philosophical implications. It touches on questions about the nature of existence, the lifespan of cosmic structures, and the ultimate destiny of all matter and energy. As our understanding of the universe deepens, we move closer to answering these fundamental questions. The study of the universe's fate is a testament to humanity's enduring curiosity and quest for knowledge. Whether the universe ends in a big freeze, big crunch, or big rip, each scenario offers a unique perspective on the cosmos. Exploring these possibilities helps us understand the fundamental forces shaping our universe. Insights into fundamental physics are essential for understanding the universe. They help explain the basic building blocks of matter and the forces that govern their interactions. The discovery of the Higgs boson was a major breakthrough. It confirmed the mechanism that gives particles mass, completing the standard model of particle physics. Research into dark matter provides clues about unknown particles. Experiments are designed to detect these particles directly or infer their properties through indirect evidence. Dark energy challenges our understanding of gravity and cosmic expansion. It suggests there may be new physics beyond the standard model and general relativity. Neutrino experiments reveal the properties of these elusive particles. Understanding neutrino masses and oscillations can answer fundamental questions about particle interactions and the early universe. Gravitational wave astronomy opens a new window into the universe. Observations of these waves provide insights into black holes, neutron stars, and the nature of spacetime. Quantum mechanics and general relativity are cornerstones of modern physics. Reconciling these theories through quantum gravity models is crucial for a unified description of the universe. String theory proposes that particles are one-dimensional strings. It aims to unify all fundamental forces, including gravity, in a single theoretical framework. Loop quantum gravity suggests that space-time is quantized. This theory offers a different approach to understanding the fundamental structure of the universe. High-energy particle collisions at accelerators like the Large Hadron Collider recreate conditions just after the Big Bang. These experiments explore fundamental forces and potential new particles. The study of black holes tests our understanding of gravity. It probes the limits of general relativity and explores quantum effects in extreme environments. Cosmic inflation theory explains the uniformity of the cosmic microwave background. It suggests a rapid expansion of the universe just after the Big Bang, driven by a high-energy field. The exploration of extra dimensions could revolutionize physics. Theories like string theory predict additional spatial dimensions that could explain fundamental particle interactions. Advances in technology and experimental techniques drive progress in fundamental physics. New instruments and methods allow scientists to test theories with unprecedented precision. Understanding fundamental physics connects the smallest scales of matter with the largest structures in the universe. It provides a deeper insight into the nature of reality and the forces that shape our cosmos. As research continues, each discovery builds on the last, expanding our knowledge and refining our theories. The quest to understand fundamental physics is a journey toward comprehending the universe in its entirety. Philosophical and existential questions arise from our study of the universe. These questions probe the nature of existence, consciousness, and the ultimate purpose of the cosmos. The origins of the universe lead to profound questions about creation. Why does anything exist at all, and what caused the universe to come into being? The concept of the multiverse challenges our understanding of reality. If multiple universes exist, what does that mean for our place in the cosmos? Time and space themselves raise deep questions. What is the nature of time, and is it infinite? Can space exist without time, or are they intrinsically linked? The search for extraterrestrial life explores our uniqueness. Are we alone in the universe, or is life a common occurrence on other planets? The study of consciousness intersects with cosmology. How does consciousness arise, and could it exist in forms beyond our current understanding? The fate of the universe prompts reflections on eternity. What does an infinite or finite universe mean for our understanding of existence and the passage of time? Free will versus determinism is another significant question. If the universe follows physical laws, to what extent are our actions determined by those laws? The nature of reality itself is a fundamental question. Are there aspects of reality that we cannot perceive or understand with our current scientific tools? Ethical considerations emerge from our technological advancements. How should we use our growing knowledge of the universe responsibly? The search for meaning in a vast universe is a central human concern. Does the universe have an inherent purpose, or do we create meaning through our experiences and actions? The interplay between science and spirituality explores different ways of understanding existence. How do scientific discoveries influence spiritual beliefs and vice versa? The idea of a cosmic beginning or end raises questions about cycles of creation and destruction. Is the universe a one-time event, or does it go through endless cycles of birth and rebirth? The potential for human colonization of other planets invites speculation about our future. What ethical and practical considerations should guide our expansion into the cosmos? Understanding our place in the universe influences our perspective on life. It shapes our worldview, our values, and our sense of connection to the cosmos. As we continue to explore the universe, these philosophical and existential questions remain central to our quest for knowledge. They remind us that science and philosophy are intertwined in the pursuit of understanding our existence and the universe. The study of cosmology contributes significantly to other scientific fields. It provides insights that help advance our understanding of physics, chemistry, and biology. In physics, cosmological research has led to the development of new theories and models. Concepts like dark matter and dark energy challenge our understanding of fundamental forces and particles. Astrophysics benefits directly from cosmological studies. Observations of cosmic phenomena such as black holes and neutron stars, provide data that refine our models of stellar evolution and high-energy processes. Cosmology also intersects with quantum mechanics. Exploring the early universe's conditions helps test theories about the behavior of particles and forces at the smallest scales. In chemistry, the study of the universe's elemental composition sheds light on nucleosynthesis. Understanding how elements formed in stars and supernovae informs our knowledge of chemical processes and the periodic table. Biology gains insights from the search for extraterrestrial life. Studying extreme environments in space, such as those on Mars or Europa, helps us understand the potential for life beyond Earth. Planetary science benefits from cosmological research by examining the formation and evolution of planets. This research helps us understand the processes that lead to the development of habitable worlds. Environmental science can draw lessons from studying other planets' atmospheres. Understanding the greenhouse effects on Venus and Mars provides context for addressing climate change on Earth. Cosmology also influences the field of geology. The study of meteorites and planetary geology informs our understanding of Earth's formation and the history of our solar system. Advances in technology driven by cosmological research often have broader applications. For example, innovations in imaging and data processing developed for space telescopes are used in medical imaging and other fields. The collaboration between cosmology and computer science has led to significant advancements. Techniques developed for analyzing large datasets from space missions are now applied in fields like artificial intelligence and machine learning. Cosmology contributes to our understanding of time and relativity. Research on time dilation and gravitational effects enhances our knowledge of fundamental physics and its practical applications, such as GPS technology. Materials science benefits from research conducted in space. Studying materials in microgravity conditions helps develop new materials with unique properties that can be used in various industries. The interdisciplinary nature of cosmological research fosters collaboration across scientific disciplines. This collaboration leads to a more integrated understanding of natural phenomena and drives innovation in multiple fields. The broader impact of cosmology extends to education and public outreach. The discoveries and questions posed by cosmology inspire curiosity and a deeper interest in science among students and the general public. Cosmology's contributions to other scientific fields highlight its fundamental role in advancing human knowledge. It demonstrates the interconnectedness of scientific inquiry and the cumulative progress of our understanding of the universe. In this video, we explored the vast and fascinating universe from its origins to its ultimate fate. We began with the Big Bang Theory, which describes the universe's expansion from a hot, dense state 13.8 billion years ago. We delved into the evidence supporting this theory, including the cosmic microwave background and the redshift of galaxies. We then discussed the inflationary period, a brief moment of rapid expansion that set the stage for the universe's current structure. This led us to the formation of fundamental particles, protons and neutrons, and the subsequent nucleosynthesis of light elements, which laid the foundation for the universe's chemical composition. Our journey continued through the cooling and expansion of the universe, leading to the formation of the first atoms and the reionization epoch. This crucial period allowed light to travel freely, shaping the large-scale structures we observe today. We also examined the role of dark matter and dark energy in the universe's expansion and structure. The discovery and significance of the cosmic microwave background were highlighted as key pieces of evidence for the Big Bang Theory. We also explored alternative theories like the steady-state theory and the Epyrotic model, which offer different perspectives on the universe's origins and evolution. Particle physics experiments and the role of particle accelerators provided insights into the fundamental particles and forces that govern the universe. These experiments, along with supercomputing in cosmology, have advanced our understanding of cosmic phenomena and the early universe. The discussion of quantum gravity models, such as string theory and loop quantum gravity, highlighted efforts to unify quantum mechanics and general relativity. These models aim to provide a deeper understanding of space-time and the fundamental structure of the universe. We also explored the philosophical and existential questions raised by cosmology, touching on the nature of reality, the origins of life, and the ultimate fate of the universe. These questions remind us of the profound implications of our scientific discoveries. The contributions of cosmology to other scientific fields were also covered, demonstrating the interconnectedness of scientific inquiry. Advances in cosmology have influenced physics, chemistry, biology, and technology, driving innovation and expanding our knowledge. Looking to the future, we discussed the exciting technological prospects in cosmology, including new telescopes, space missions, and advancements in particle physics and supercomputing. These innovations promise to push the boundaries of our understanding even further. If you enjoyed this comprehensive journey through the universe, please like and subscribe to our channel. Don't forget to check out our other videos for more fascinating explorations into the mysteries of the cosmos. Your support helps us continue to bring you the latest discoveries and insights in the world of science. Thank you for watching, and we'll see you in the next video.